Good morning, students. My name is Shankar. Today, we are covering GATE Power Electronics revision in a marathon session as we are conducting at Home Institute. I hope you already see the previous subjects. Now, today, we are going to cover power electronics. So, this total power electronics syllabus I covered into four chapters mainly. Of course, there is a fifth chapter also. Officially, that fifth chapter is not in the syllabus, but in the previous gate exam there are few questions on that, so at the end I will touch that also. So the prerequisite for this video is in our Open Institute YouTube channel. There is um, I think 2 3 years back I covered a revision video on entire power electronics. So based on theoretical point of view I covered it. So before watching this video, as I already announced in the announcement video, I told please watch that section first and then come to here. Even if you not covered that also, you can watch this and later on that also. So in that I explained all the concepts through different equations, waveforms, diagrams and all. So in this video mainly I will keep it as simple as possible. So mostly we are going to cover this topic through questions, especially okay, like objective questions or numerical answer type questions. So this is what we are going to do. It will take around 4.5 to 5 hours of the session. So am I audible? Is it fine, everything from your side? If you have any issues regarding the stream, online streaming, please let me know. Regarding the screen and my audio, if you please uh, say yes, then we will move forward. Otherwise, I will try to resolve if there is any issue. Okay. All right. Now let us move forward. So coming to GATE triple E paper or electrical engineering paper, this power electronics is one of the very important subject. Not only from examination point of view, this subject is useful and very important from interview standpoint as well, because in when you're going for MTech admission into IITs or NITs, MTech in power electronics is a very demanding subject. So this will be very useful and important also. The total syllabus as per my teaching, I divided into four chapters. Okay, the first chapter is, I hope, because this is a revision, I hope all of you have your short notes. Just sit with that short notes and just go through all of my statements. The total syllabus is divided into four topics, like first chapter basics and power semiconductor devices. The second chapter is rectifiers. Even i I said it is a rectifiers one chapter, but it is a little lengthy chapter. So in this video I'm going to split into the two parts again, 2a, chapter 2a and chapter 2b. Chapter 2a we are going to cover single phase rectifiers, and chapter 2b we are going to cover three phase rectifiers. All the concepts in this video we are going to cover through some questions. I will take one question. That question can be some conceptual question or from PYQ. Either in the PYQ again 1 mark as well as 2 marks questions, and based on that I will give some background of the question and what are the important areas that you have to focus on this. So to make the video simple and interesting, I selected important and some simple questions as well, to make the subject to be very smooth. And the third chapter we are going to cover is the DC to DC converters, and the fourth chapter is DC to AC converters, that is the inverters. At the end there are a couple of questions from AC voltage regulators. What to cover in that we will very briefly review in that. So at the end of chapter 2a we are going to take a short break. 2a or 2b depends on the time. Around 11:30 I will give you break for 15 to 20 minutes, and then we will proceed. So this is what the overall agenda for today. So in chapter 1, what are the key areas that you have to focus? Okay, so the key areas are in chapter 1, the key areas are, just a minute guys. In chapter 1, the key topics are Fourier series. Even for Fourier series analysis also, you just need to understand three waveforms. For three waveforms, you should look into Fourier series. What are that three waveforms? One is a square waveform, and delayed square waveform, and quasi square waveform. So for these three waveforms, the basic thing is you have to understand the Fourier series equations. Again, why do we need to give more importance for Fourier series analysis in power electronics subject? The reason is, I'm sorry, just a minute, students. Just a minute, we lost this. So we need Fourier series expressions. They are square, delayed square, and quasi square. Now, what I asked here, the question is, why do we need to give more importance for Fourier series analysis in this power electronics subject? The main reason is power electronics circuit is simply nothing but it will deal with the conversion and control of electrical power in an efficient manner. For that, we will use power semiconductor devices. These power semiconductor devices will operate as those switches. Okay, because of the switching operation, the waveforms will be modified from sinusoidal to non-sinusoidal nature. Okay, so am I audible, guys? Voice is fine. Okay, so when because of the switching action, when the waveforms are modified to non-sinusoidal waveforms, then there will be a concept of Fourier series analysis. As per the Fourier series analysis, the waveforms will have fundamental component and along with some harmonics. So what type of harmonics are there, that we have to focus into that. Okay, now after second important area is you should learn how to find average and RMS values of some standard waveforms. First chapter, I am writing the concepts, what you have to look more focused way. So you need to learn how to find average and RMS values. In this video, we are not going into how to calculate all those things, but as and when required, I will give more emphasis to that. And the second category is a switch classification. For GATE exam, this switch classification is very, very important. Switch classification. Switch classification is very important. Even we have some questions as well. After that, devices overview. Devices overview in a brief manner. As this is the revision session, we will not go into much deeper into device physics. Even power electronics, there is no need also. For GATE exam, only thing you need to focus from the first chapter, how to find average and RMS values for certain standard waveforms, and what is the switch classification, and what about the devices overview. Now coming to square waveform. First let me write down what is the Fourier series equation. So if you have your short notes and all, you try to along with me, you please if you have a short notes, probably you might already prepared during your preparation. Try to tell me or try to write down on your notebook or notepad what is a Fourier series equation for a square waveform. So in a simple way, I will just show you what is a square waveform here. So if you take a square waveform like this, x-axis is omega t. Okay. Now say for example this let us call this function as x of t. For this x of t, this square function will have all odd harmonics. And suppose if the square waveform magnitude is 4x divided by n pi sine of n omega t. This is a Fourier series expression for square waveform. Okay. Now in this, what are the key things that we need to remember from examination point of view? So this power electronics subject, Fourier series equation for this square waveform has a lot of importance, because later on in the converter analysis you will get this Fourier series equation multiple times. Okay, so what are the important things? Anyhow, there are, I am going to write Fourier series equation for 3 waveforms. At the time I will give common conclusions. Now the next important waveform is delayed square waveform. Next important waveform is delayed square waveform. So delayed square waveform means here also the same square waveform only, but it will start from some angle alpha. Okay, so here x-axis is omega t. So this angle is alpha. So square waveform started after some angle alpha. Okay. Right. Now for this square waveform, what is the Fourier series equation. Say for example, let me call it x of t. Let us say the square waveform magnitude is capital X. In this case also, the waveform will have odd harmonics. Anyhow, in the revision session, this is not the forum to discuss all the derivations of this. 4x divided by n pi sine of n into omega t minus alpha. Sine of n into omega t minus alpha. Okay. So this is a Fourier series expression for a square waveform started after some angle alpha. Okay. And quasi square waveform. The third important waveform is quasi square waveform. This is very important waveform. Okay. And this quasi square waveform, it looks like this. Quasi square means the waveform will have a equal amount of pulse duration in both positive as well as negative half cycles, and it will have, let us say this is the alpha and this is pi plus alpha, and 2 pi here. And this is the 2 pi, and here it is the 2 pi plus alpha. Okay. Now for this quasi square waveform, now you please recollect what is the Fourier series expression. You please type in the chat window. So Fourier series expression will be, let us say x of t is equal to sigma odd numbers of n 4x divided by n pi cos of n into alpha by 2. Up to here, that is a magnitude of nth harmonic component multiplied with sine of n into omega t minus alpha by 2. Sine of n into omega t minus alpha by 2. So these three equations, minimum things that you have to remember. No need to look into all Fourier series equations for various waveforms that you will study in a signals and system subject. Coming to power electronics subject, these three equations are minimum thing that you have to remember. Okay. Now, what are common things? Just for a revision point of view, these things you have to correlate. So what are the common things in all the three waveforms? The three waveforms, DC component is equal to 0. There is no DC component in the waveform. Okay. And even harmonics are absent. Even harmonics are absent. And the third thing is only odd harmonics are present. Only odd harmonics are present. Okay. Only odd harmonics are present. So these are the three important common conclusions that you need to remember for these three waveforms, Fourier series equations. And what is the fundamental component? If you remember these equations, we can answer any type of questions. Now, on these things, let us take one question. Now, here there is one, of course, this question is given in GATE 2018. Remember, guys, if you practice all previous GATE questions on quasi square waveform, you will have at least 4-5 GATE questions on particularly quasi square waveform. Now, let us read the question. The waveform of the current drawn by a semi-converter, of course, source current waveform of semi-converter is a quasi square waveform that anyhow we will revise in the semi-converter topic. from a sinusoidal AC voltage source is shown in the figure. If I naught is equal to 20 ampere, what is the RMS value of fundamental component of the current? Okay, so first what you have to calculate now, first calculate what is the peak value of fundamental component. If you look back into the equation up to this part, peak value of the fundamental component. In this case, in the place of x, I have to substitute I naught magnitude, that is given as a 20 ampere. Therefore, what is the magnitude here? 4 into 20 divided by 5. Okay, where n is equal to 1. Fundamental we are looking. Multiplied with cos of n into alpha by 2. Here alpha is given as a 30 degree. Therefore, 30 degree divided by 2. This is a peak value of the fundamental component. Now, RMS value of this fundamental component is IS1 RMS is equal to IS1 peak divided by root 2. IS1 peak divided by root 2. So, that will be 4 into 20 divided by pi root 2 multiplied with cos 15 degree. Okay, so if you calculate, this value is around 17.4 ampere. So this is RMS value of the fundamental component of the given waveform, the given quasi square waveform. Okay, so students, first of all, you just leave the in your mind, leave that hack. Power electronics is a difficult subject. I selected out of this, of course, few questions will be very conceptual based. I will agree that, but not all the questions. Suppose if you get 4 or 5 questions from power electronics, definitely you can answer 3 to 4 questions. Okay, either 1 or 2 questions will be little difficult, but instead of worrying about that 1 or 2 questions, you focus on the majority of the questions. Okay, now see here, if you remember only one formula, you can answer this question. This is a gate question only. All right, so in this what you have to do, you need to first concept is you should practice Fourier series equations for 3 waveforms. One is a square, delayed square waveform and quasi square waveform. Okay, now let us look into the switches. Let us look into different types of switches. Okay, this is a very important topic, switch classification. Even I will not go with all the explanations part. Switch classification. Okay, so if you have this switch classification, that is a very important and useful also. The first classification is based on based on control feature. Based on control feature. Okay, now I will give you what are the different types of switches based on this control feature. I want you to give me the answers. Okay, now the first type is uncontrolled switch. First one is uncontrolled switch. Now can you please give me an example for this? Please give me answer in chat window. Uncontrolled switch, the example is diode. Uncontrolled switch, the example is the diode. The second one is semi or half controlled switch. What do you mean by semi or half controlled switch? That means for this switch, we can control only on state, and a turn off state cannot be controlled. The example for this type of switch is, we can take SCR. And third category, third type of switch is third type of switch is fully controlled switch. Third category is the fully controlled switch. In this, GTO is one example. Fully controlled switch means the both on and off states can be controlled from the same control terminal, okay. That is an example is a GTO. And second category is all transistor family devices. All transistor family devices. What are these devices? BJT, MOSFET and IGBT. BJT, MOSFET and IGBT. Now in this, BJT is current controlled device. MOSFET and IGBT are voltage controlled devices. MOSFET and IGBT are voltage controlled devices. Okay. Next. Now this classification is based on control properties. Next, based on steady state operating points. Based on steady state operating points. Based on steady state operating points, the first category is unipolar switch. Unipolar switch. Example for this, diode and transistor family devices. What do you mean by unipolar device? Unipolar switches, during turn off condition, these switches can block only one polarity of the voltage. Now the second category is bipolar switch. The second category is bipolar switch. What are the bipolar switch? An example, SCR, GTO and triac. In a simple words, you can also say these devices together treated as thyristor family devices. Okay. Now based on the switch classification, I will give you I will take one PYQ as an example, but you can see in the PYQ questions you will have 6 to 7 questions from only this topic. So this is very, very important, especially for GATE exam, and every time these questions we are getting. Now next one is unidirectional switch. Unidirectional switch. Okay. So unidirectional switches, you can take all devices except triac, because the triac will come under the next category, that is the bidirectional switch. Triac will come under bidirectional switch. So triac. So depends on different combinations. You can select what type of switch and all. But there is a one more important conclusion you have to take. For a given application, what type of device you have to select? What type of device you have to select? Okay, so that is low power application. Instead of this, let me write like this. This table, students, if you understand this table, you can answer multiple questions. Even from this table also, there are 5 to 6 PYQs. Power capacity. Power capacity and switching frequency capability. Switching frequency capability. Okay, so SCR and GTO. SCR and GTO. Next one, MOSFET. Next, IGBT. And next one, triac. So if you are able to give the answers for this table, most of the questions you can answer it. So in sometimes in the gate exam also, you will have a questions like some application will be given. Even in the recent gate also there is a question. So and so application, like there is a laptop, you have a laptop, there is a charging circuit for that. For that charging circuit, you have to use a device which can be operated with high frequency application. Which of the following device is best suitable? So you can answer such type of questions by understanding this table. SCR and GTOs are preferable for high power applications. Whenever a device is operating with a high power, you cannot operate with a high switching frequency. High power and low switching frequencies, SCR and GTOs are preferable. MOSFET is preferable for high switching frequencies. MOSFET is MOSFET is the only device in the entire power electronics category you can use MOSFET for high switching frequencies. Suppose the best example is SMPS circuits. Which of the following device is best suitable? And in the regulated power supplies, like a charging circuits and also high switching, wherever you feel that the application has the high switching frequency, then you have to select MOSFET. And when the switching frequency is high, by default the power handling capacity will be low. Okay, and IGBT is preferable for medium power and medium switching frequency capability. Triac is the only device that will have low power as well as low switching frequency application. So best example for that category will be, best example for this category will be fan regulators. Okay, fan regulators. So I will write down one more very important conclusion also. SMPS circuits. Of course, SMPS circuits are not in the gate syllabus, but this is an application point of view. SMPS circuits, you have to use MOSFET, and fan regulators, low power and low switching frequency, you have to use the triac is the main device. Okay, so these are very important conclusions, right? Now let us take one or two PYQs. Now see this one. The question is, a semiconductor switch needs to block voltage V of only one polarity during off state as shown in this figure. Okay, here. So what do you mean by this? This means we need unipolar blocking. We need unipolar blocking. Next, and carry current in both directions during on state as shown in the figure 2. That means when the switch is in the turn on state, it has to carry current in both the directions. That means you need bidirectional switch. You need you need bidirectional switch. So from the given four options, of course this is the MSQ, this question has more than one answer. We need to select unipolar and bidirectional switch. Okay, you need a unipolar and bidirectional switch. So before answering this question, now if you look into, let us examine each option one by one. Now a transistor with an anti-parallel diode, it can block voltage and current like this. It can block voltage of one polarity. All transistor family devices belongs to unipolar switches. They can carry the current in both the directions. Therefore, option A will be suitable for our question. Okay. Now, but this switch has no proper thing. Why? Because this switch, for example, it cannot carry the current in this direction. It cannot carry like this because this diode will stop this one, and but this device can carry current from Q to P. So this device can carry the current only one direction, but we need both the directions of current. So this option is violated. It is not suitable. And in this case, this device can carry the current only in this direction, but in this direction it is not possible. So option C also not suitable for the given question. Okay. Now if you see this one, in this case current can flow in this direction, and in this direction also it can carry. Okay. So this switch will be suitable for unipolar and bidirectional switch. Because of this transistor, it can block one polarity of the voltage. Therefore, for this question, the suitable answer will be A and D. For this question, the suitable answer will be A and D. So students, switch classification is very, very important. So whether you have to select unipolar bidirectional switch or bipolar unidirectional switch, apart from this, there are 5-6 PYQs also. I will suggest you to practice that questions as well. Okay. This is a quick recap from switches standpoint. Switches standpoint, right? Now, let us move to the next one. All right. Now, another very important thing that I observed from the PYQs is how to calculate switch losses. Okay, how to calculate switch losses. So, energy loss, simple formula is energy loss E is equal to integration from 0 to Ts, voltage across the switch multiplied with current flowing through the switch. Suppose in some questions, the question is only find switching loss during turn on transition. Okay. And sometimes you'll have a question, find switching energy loss only during turn off transition. In that case, you have to take only that interval. But in the overall cases means you have to take complete thing, right? And switching power loss. Switching power loss is equal to 1 by Ts integration from 0 to Ts voltage across the switch into current flowing through the switch dt. Okay, this is about switching power loss. So you can also write one more expression here. 1 by Ts is nothing but Fs multiplied with this integration is energy loss during switching transition. So switching power loss, you can also express it as a switching frequency multiplied with switching energy loss. Now, what are the important things that you need to remember in this case? Suppose I will show you one particular case. This is, let us say, current, and this is the voltage. Okay, that is the voltage. Now let us say this interval is let us say this is the T1. Now in this particular case, energy loss, you can express it as Vi divided by 6 into this transition period. This transition period. Okay, this is the one model. That means when voltage and current both are having linear transition, one is linearly falling, another is the linearly increasing. You will come across one more case, that is voltage is falling, current is constant. This is the I and this is V. In this case, again, let me take here this interval, the transition period will be T2. In this case, the energy loss will be Vi divided by 2 into transition period. Whatever the time is given in the question, you can take that value. So, in order to find the switching losses, these two formulas are more than sufficient. These two formulas are more than sufficient. Okay. So in this video, I'm trying to simplify the subject. So again, in this 4 to 5 hours of session, it is not possible to cover all the equations with the derivations. Even I don't want to go with the waveforms also in this analysis. It is a big challenging for me also to cover without waveforms this power electronics session, because in usual classes, I will take around 85 to 90 hours of the section. Now let us see. Let us take one PYQ from this model. Now see this question. The voltage across and the current through a semiconductor switch during a turn-on transition are shown in the figure. The energy dissipated during the turn-on transition in millijoule is. Okay. So if you see here, the entire turn-on transition is divided into two portions. One is during T1, another is during T2 interval. Suppose let us calculate these two energy losses in these two intervals separately. Now say for example, if I take this instant as T is equal to 0, then this instant I can say that it will be T is equal to T1. This instant will be T is equal to T1. Okay, for during the T1 interval. Now for the second interval, suppose if I take this instant as T is equal to 0, and this instant could be T is equal to T2. T is equal to T2. Therefore, let us take here during T1 interval. Okay, during T1 interval. So E1 is equal to integral 0 to T1 voltage across the switch into current flowing through the switch dt. Okay, so now the important concept is, if you observe the given transition waveforms very closely during T1 interval, you will notice that voltage is a constant, that is of 600 volt. Therefore, if I take that 600 common here, 0 to T1 and current flowing through the switch dt, right? Now, interestingly, you will notice the integration, as I took 600 outside, the remaining integration part, I can tell that this is area of this current triangle, right? Area of that current triangle. Therefore, what is the formula for area of a triangle? Half into height of the triangle, that is 150, into base of the triangle, 1 microsecond. That means 10 power minus 6. Therefore, from this, you will get E1 is equal to 45 millijoule. E1 is equal to 45 millijoule. So the thing is, you need to understand the logic. Power electronics questions, it's not so difficult. Only thing, you should understand the waveform. You should digest the waveform well, and from that you should able to apply the mathematics very simplified manner. Similarly, during T2, during T2, so E2 is equal to integration from 0 to T2, voltage across the switch into current flowing through the switch. Again, same definition. Definition wise, there is no difference. But now, in the second half, in the second interval, what is your observation? The observation is current is constant now. What is the constant value of the current? That is 100. So, if you take that 100 outside, the remaining integration will be integral 0 to T2, voltage across the switch dt. Voltage across the switch dt. Now, just like earlier, that integration is equivalent of area of voltage triangle, isn't it? Area of this voltage triangle. That will give you 1 by 2 into height of the triangle is 600, base of the triangle is 10 power minus 6. So, this will give you E2 is equal to, this is equal to 30 millijoule, that is 30 millijoule. Therefore, now the total energy loss, total energy loss E is equal to E1 plus E2. This will give you 75 millijoule. Total energy loss will be 75 millijoule. Now, as this question is this question is NAT base, the answer is what is the energy dissipated during turn-on transition in millijoule. What will be your answer here? Answer is simply 75. Answer is simply 75. So, students, so far, is it good? Is it going smooth? Please just tell me in the chat window. Yes, all right. Now, thank you. Thank you for sharing. Now, let us move further. All right. Now, here, this question is based on SCR concept. Okay, SCR concept. Let me give you a few base thing here about SCR. SCR is one of the important topic. SCR, I will ask few questions. Now, can you please tell me what type of SCR, what type of switch it is? What type of switch it is? Means earlier we classified a switch into two ways. One is based on control property and based on steady state operating point. From that standpoint, what type of switch SCR is? Bipolar unidirectional, that is correct answer. From the control point of view, what type of switch it is? From the control point of view, what type of switch it is? Uncontrolled, semi-controlled or fully controlled? What type of switch it is? Even there is one gate question also. SCR is considered as dash type of switch because bipolar unidirectional, it is fine. Yeah, the answer is semi-controlled switch. That is correct. So SCR is considered as a semi-controlled switch. There is one gate PYQ also. The main reason is SCR can be turned on with the gate current, but it cannot turn off with the gate current. Okay. So SCR is, as you rightly said, it is bipolar and unidirectional switch. It is bipolar and unidirectional switch, and it is semi-controlled switch. It is a semi-controlled switch. The reason is it can turn on with gate current. It can turn on with gate current, but cannot turn off, with the gate current. So that is the reason. Next, this device is also considered as latching device. Latching device. Why it is considered as a latching device? Because SCR requires gate current. SCR requires gate current until anode current crosses latching current. Okay, so it requires gate current until anode current is greater than or equal to latching current. Okay, SCR requires a gate current. In order to turn on SCR, it requires gate current until anode current is greater than or equal to latching current. So these points are sufficient to solve the next question. Now let us read this question. An SCR having a turn on time of 5 microsecond, latching current of 50 milliampere and holding current of 40 milliampere. So for this question, we need latching current, that is given as 50 milliampere. That is given as a 50 milliampere. Is triggered by a short duration pulse and is used in the circuit shown in the figure. Find the minimum pulse width required to turn on this SCRs. Now, students, same model, I selected a PYQs in such a way that similar model repeated multiple times. So that means there are high probability of getting that type of question. So whenever you are doing PYQs, don't do blindly in a random order. Okay, so you club similar concepts of the questions and solve it together. Of course, that need a little bit practice and little experience also. So when you are not able to collect the similar conceptual questions, you take the help of experienced people like faculties or your seniors also can take the suggestion. So the similar model, there are two questions. I selected only one here. After this session, you try to figure out that question and try to do it. Now, what we need to find the minimum pulse width required to turn on this SCR. How long we should supply gate current until anode current is greater than latching current. So what we will do, let us assume SCR is already turned on by giving suitable gate current. Okay, SCR is already turned on by giving suitable gate current. Suppose if SCR is turned on, if SCR is on by applying suitable gate current, then the equivalent circuit will be SCR is turned on. So I will replace SCR with a closed switch. There is an RL circuit here. There is a 5 kilo ohm of resistance given. There is a 5 kilo ohm of resistance given. Okay. Now, what is current flowing through this branch in this case? That 100 volt is directly applied here. Then this is a 5 kilo ohm. Therefore, the current flowing through this 5 kilo ohm branch will be 20 milliampere. At the time of triggering the SCR, gate current pulse is removed. Okay. For SCR to turn on suitably, how much current that has to flow through this SCR? Minimum value of the latching current. Latching current is given 50 milliampere. Therefore, by applying KCL, this current should be 30 milliampere. Okay, that current will be 30 milliampere. So, if you apply this 30 milliampere, how to equate it? 30 milliampere can be equated to the current flowing through RL branch. What is the expression for RL branch current? VDC, source voltage divided by load resistance, into 1 minus e power minus t divided by L by R. Minus t divided by L by R. Now, if you substitute the data points here, source voltage is 100 volt and the the load resistance here is 20 ohm into 1 minus e power minus t. We want that t value only, and inductance value is 0.5 Henry divided by resistance value is 20 ohm. So, by solving this, we get t is equal to, can you please tell me what could be the answer for this? 150 microsecond. That is the correct answer. microsecond. Okay. So, in this first chapter, again, I am quickly revising. What are the important things that you need to practice in the first chapter? Students, can you share it in the chat window? What are the few important topics that we need to practice in first chapter? At least through this session, what you learned here. Fourier series one thing. Next, switches, losses, classification of switches, correct? Types of switches, all right, all right. All answers are correct, students. Just 1 minute, let me check whether, uh, is the session going smooth or you're facing any issues? Okay, all right. Now, yeah, at Home Institute, this slide explains about different courses that we are starting in the offline summer. The dates are 13th May, 23rd May 2026, and 3rd June and 17th June, right? So, if anyone is watching this session recording, you can just pause the video and you can look into the dates and all. So, fee details and course particulars, everything is mentioned in the screen. Okay. Now, let us move further. Chapter 2a. So this chapter 2, basically I used to cover in the class as a rectifiers, altogether a single chapter, but now in this session I divided into two parts. Chapter 2a chapter 2a, that is a single phase rectifiers we will cover now. After that we will take three phase rectifiers. Okay, now here in this single phase the rectifiers, what are the different topics that we are going to look here. Again, just like earlier, I will write down the topics in one order. You can see single phase, half wave, uncontrolled rectifiers. What are important things that revise? Okay. The first thing is single phase, half wave, uncontrolled rectifier. In this case, the basic thing is you should look into resist to load. So what are the important things in the resist to load that you have to see? Anyhow, you need to understand the waveform analysis that we are not going to do here. So in case of resist to load, the minimum things that you need to remember, what is the conduction angle of the device, and what is the average output voltage, what is the average output current formula, and power delivered to the load, of course input power factor. These are the things that you have to remember. And the next one is pure inductive load. Pure inductive load. So pure inductive load is very important case. Pure inductive load is, this is a very important. Pure inductive load is a very important. So in the pure inductive load, how to analyze the circuit? Only one statement. How much time inductor will take to store energy? It will take same time to release that energy as well, right? Because of the sinusoidal source. We'll take different cases that we'll study one by one. The next one is RE load. In case of RE load, the important questions that you can expect: how much time the device will conduct, how much time that device will conduct, and average charging current drawn by the load. These two things are important. Now, single phase, half wave, uncontrolled rectifier, these are important. Of course, the next one is a RL load as well. Okay. Now we have resist to load, pure inductive load, RE load. So far in PYQs the questions. RL load basically it came in the phase control rectifiers. Now these are the loads that you have to focus. Next, single phase, half wave, phase controlled rectifier. And pure inductive load, pure inductive load, RL load, RL load with freewheeling diode and RE load. Only thing is, in all the cases, what are the important things that you need to remember? I will write down here. Only your focus will be on, focus on conduction angle or time, conduction angle or time, conduction time of the device. Next, average output voltage and output current. Enough. These two things you should focus. For each circuit, if you prepare short notes in line with this, so more than enough. Okay. Next one, single phase, full wave rectifier circuits. Single phase, full wave rectifier. single phase full wave rectifier. Now I am going to cover all the circuits by one PYQs so that you will cover it. Yeah, very good. Vijay Kumar, peak inverse voltage, very good. And also peak inverse voltage, thank you for reminding. Yeah, I really encourage that type of discussion, even if I miss anything, because in the regular class it will come in the smooth flow. If I miss anything, you please raise a point like that. Thank you so much. All right. Now, single phase full wave rectifier. Single phase full wave rectifier, the first topology, that you can take is the midpoint converter. The first thing that you can consider is the midpoint converter. Okay. Second one, single phase full converter. Single phase full converter. Third one, single phase half controlled rectifier, or single phase semi converter. Single phase half controlled rectifier and a single phase semi converter. In single phase semi converter, again we have three topologies. One is symmetric configuration, and the second one is asymmetric configuration, and the third one is single phase full converter with freewheeling diode. Single phase full converter with freewheeling diode. Okay, so these are different circuits that we need to focus. Now I will touch each and every circuit with some PYQ. All right. now let us see this question. In the circuit shown in figure, the diode used is ideal. What is the input power factor? Okay, now if you just look into the definition for input power factor, I can write it like this: power delivered to the load divided by source volt ampere, isn't it? Power delivered to the load divided by source volt ampere. As the load is resistive, this power delivered to the load, you can express it as VOR square divided by R. Denominator, source volt ampere, Vs multiplied with what is Is? So in half wave rectifier circuit, as per the circuit concept, I can say that Is is equal to I naught. Is is equal to I naught. Students, here sometimes you may feel that I explained the question in 10-20 minutes. Some students are worrying, as a faculty is explaining in the video 10-20 minutes, how can we answer the question in the exam within 1 or 2 minutes? The 10-20 minutes is, I am not doing that. If I see the question immediately, I can directly get the answer, okay, based on my preparation and my experience. But we will take 5-10 minutes to explain you the concept. But in the regular class, what we used to do, we will explain the theory first and we will do the question. For question, it will take 1 or 2 minutes only. As the question is explaining through concept, it will take more time. So because in our earlier online live session, I get some questions. One faculty explained one question or one concept 10-15 minutes. How can we answer the within 1 minute in the exam hall? The point is, as I'm explaining, otherwise direct formula is there for this particular question. So for this half-wave rectifier circuit, source current is equal to output current. What do you mean by that? Is is equal to I naught. Therefore, RMS value of the source current is equal to RMS value of the output current, where RMS value of the output current, because of the resistive load, it is simply RMS output voltage divided by load resistance. Okay, so I can substitute here VOR divided by R. So simplification, I can cancel this R here. One VOR also can be cancelled. Therefore, finally I will have input power factor is equal to RMS voltage, RMS output voltage divided by RMS value of the source voltage. Now, for this half-wave rectifier, can you please tell me what is RMS value of the output voltage? For half-wave rectifier circuit, what is the RMS value of the output voltage? Please tell me, guys. Half-wave rectifier circuit, RMS value of the output voltage. VOR. Vm by 2, that's correct answer. Vm by 2. So if I substitute here Vm by 2 in the numerator, what is RMS value of the source voltage? Vm divided by root 2. Therefore, Vm will cancel. Vm will cancel. Okay, so input power factor is equal to 1 by root 2. 0.707 lagging. Power factor, input power factor of rectifier circuit is always lagging. Power factor, input rectifier. See, one more thing. For any rectifier circuit, power factor is always calculated at the input side, not at the output side. The reason is input is AC side, output is the DC side. DC side generally will not find out power factor. Okay. Now, one more thing. Power factor of any rectifier circuit is always lagging. Why? Because of source current harmonics. That is also an important thing that we will look into in the later questions. So for this, answer is 1 by root 2, whose numerical value is 0.707 lagging. Okay, next. Now, this is a pure inductor load. It's a very, very important question. This question came in GATE 2007. In the circuit of adjacent figure, the diode connects to the AC through a pure inductance L. How much time the diode conducts? How much time the diode conducts? I hope this is a very important question for regular students who is practicing power electronics. You will get answer for this question easily. Answer D. Okay, so answer D. So what other questions that we can expect from this? What other questions we can expect from this? So in this question, I can say conduction angle of the diode will be 360 degree. Diode will never turn off in this particular case. What is the reason for that? From 0 to pi, diode will store energy. Who will supply that energy? I'm sorry, inductor will store energy. Who will supply that? Source will supply. So let me write down here. From 0 to pi, inductor stores energy. Pi to 2 pi, inductor releases energy. Therefore, diode will conduct in a complete cycle. Okay. Now, you can also get in this circuit, you should also prepare these questions in this circuit. What is the expression for output current? Vm divided by omega L into 1 minus cos omega t. Okay, this is also one of the expected questions. See, the practicing PYQs, especially in the revision stage, you should also practice like this. Okay, so what is that? Now in this question, in this PYQ, question is only about conduction angle. Now during your revision, you just take a moment, close your eyes. What other questions that I can expect from this circuit? Of course, they're not part of this question. Tomorrow you can, suppose if I prepare a question paper, this question is already given. I would like to give the same circuit, but what other questions I can ask from this one? What is the expression for output current? Correct? And what is the peak value of the output current? So I naught is peak at omega t is equal to pi. Output current is peak value at omega t is equal to pi. Therefore, suppose tomorrow if the question is what is the peak instantaneous value of the output current, that you can substitute by substituting omega t is equal to pi, you will get peak output current will be 2 Vm divided by omega L. You can also have a questions on this circuit. What is the average value of output current? That is Vm by omega L. Peak output current divided by 2. What is RMS value of the output current? Vm by omega L into root of 3 by 2. Root of 3 by 2 numerical value 1.225 into, in the place of Pm by omega L, I can write average output current. So these are the ways you can recollect from different things. Now, sometimes you can also have a question like this. In the same circuit, suppose if I connected an ammeter here, that ammeter is moving coil instrument, what is the reading of that? If the ammeter is MI instrument, what is the reading of that? Moving coil means average value, Vm by omega L is the answer. If the ammeter is moving iron instrument, it will read RMS value, Vm by omega L into root of 3 by 2. So, if any one circuit is given, this is the way you have to spread across or expand the scope of the question. So, if you prepare like that, tomorrow you will be ready to answer any question. So, this is the way generally you have to prepare. You can apply this concept not only for power electronics, for other subjects also you can practice. Right? Now, let us move forward. All right, now whatever formulas I wrote earlier, one of the formula is applicable for the next question. So, all right, first let me do 8th question and then we'll come back to 7th question. A half wave thyristor. Now see here, instead of diode earlier, pure inductive load, source is sinusoidal, load is pure inductor. Now instead of diode, now it is replaced with the SCR. It is replaced with the SCR. Now can you try this question? A half wave thyristor converter supplies a purely inductive load as shown in the figure. If the triggering angle of the thyristor is 120 degree, what is the extinction angle? What is the extinction angle? Again, only you have to identify is inductor stores energy. Inductor stores energy from 120 to 180 degree. Inductor stores energy from 120 to 180 degree. So how much time it stores energy? It stores energy for a period of 60 degree. Next. Now inductor releases energy, inductor releases energy from 180 to, it stores energy for a period of 60 degree, it will release energy in another 60 degree. So 180 to 240 degree. Okay, therefore it releases energy in another 60 degree. Therefore, what is a extinction angle, right? So this will be extinction angle beta. Option A is the correct answer for this question. Suppose in this question, now I want you to answer. What other question I can ask tomorrow? Suppose if I want to give the same question in the exam, what other I can ask? What other question I can ask? I can ask, what is the conduction angle of SCR? What is conduction angle of SCR? Can you please tell me? 60 degree inductor stores energy, 60 degree inductor releases energy. Therefore, SCR will conduct for a period of 120 degree. Therefore, for this question, conduction angle for SCR will be 120 degree. Extinction angle of the load current will be 240 degree. Very good, very good. Now let us move to back. Let us come back. Now this question: a diode circuit feeds an ideal inductor as shown in the figure. Given source voltage 100 sin omega t, where omega is equal to 10 pi. This is not 10 pi. I'm sorry, this is a mistake. It is 100 pi. 100 pi radian per second. Inductance value is 31.833 millihenry. The initial value of inductor current is 0. The switch is closed at 2.5 millisecond. Okay. What is the peak value of inductor current? Now, 100 pi omega is equal to 100 pi. That means frequency is equal to 50 hertz. I hope this is clear. If the frequency is 50 hertz, 2 pi radian is same as 20 millisecond. Correct? 2 pi radian is equal to 20 millisecond. On that basis, 2.5 millisecond is equivalent of 5 by 4 radian. 2.5 millisecond is equivalent of pi by 4 radian. Therefore, this particular section, the switch is closed at 2.5 millisecond along with the diode. This particular section is equivalent of SCR with alpha is equal to pi by 4. That's all. If you are able to connect like this question is very simple. Otherwise, you have to do a lot of analysis. So, now what is this? Source voltage sinusoidal, load is pure inductor, device is SCR, where SCR is triggered at pi by 4. This question is same as question number 8, what we discussed earlier. Now, in this case, expression for output current will be Vm divided by omega L into cos alpha minus cos omega t. Cos alpha minus cos omega t. In this equation, indirectly it is given alpha is equal to pi by 4. Alpha is equal to pi by 4. Now, the next question. At what instant the current is maximum? Output current is peak value. IO peak, or let us write like this. I naught is peak. I naught is peak at omega t is equal to pi. That's it. So in that output current equation, alpha is equal to pi by 4 and omega t is equal to pi. Now substitute this one. IO peak is equal to 100 divided by omega 100 pi, inductance value 31.833 millihenry. So you can write 1000 in the numerator multiplied with alpha pi by 4 cos alpha, so 1 by root 2 minus cos pi. Cos pi is minus 1. So if you calculate this, can you please give me answer? You will get peak value of the output current, which is nothing but inductor current. So answer is a 17.07 ampere. .07 ampere. Okay, so this is the answer. Right. Now let us move to the next question. Eighth one we already completed. Now this one. A battery of EMF 150 volt with a series resistance of 8 ohm is charging through a single phase half wave phase controlled rectifier from 230 volt 50 hertz source. The thyristor is triggered with 35 degree. Determine average charging current drawn by the battery. Okay, so first let us draw circuit diagram for this. In this case, sinusoidal source SCR, load is RE type, and the source voltage is 230 volt 50 hertz. This is the NSCR. Load resistance is 8 ohm and the battery EMF is 150 volt. Battery EMF is 150 volt. Okay. So the first thing you need to calculate is you have to calculate is the theta. What is expression for theta? Sine inverse E divided by Vm, where E is nothing but 150. So this will give you sine inverse 150 divided by 230 root 2. Sine inverse 150 divided by 230 root 2. I think this value will be 27.46 degree. Okay, this is the 27.46 degree, and thyristor is triggered at 35 degree. Alpha is given 35 degree. Now we need to calculate what is the average charging current drawn by the battery. Therefore, what is the equation for this? 1 by 2 pi integration from alpha to pi minus theta, because SCR will start conduction from alpha and it will conduct up to pi minus theta. Therefore, alpha to pi minus theta Vm sin omega t minus E divided by R. Integration is with respect to omega t. So if you simplify this, you will get one by 2 pi R Vm into cos theta plus cos alpha minus E into pi minus theta minus alpha. This is the expression for I naught. So in this, theta value is 27.46 degree, alpha is 35 degree, and the load EMF is 150. And if you substitute all of these values, I calculated readily. Question number 9, I naught value you will get 4.92 ampere. This is the expression for average charging current drawn by the battery. Okay. Now, second question. PIV rating of device. This is another important calculation. What is the peak inverse voltage for this circuit? That is E plus Vm. That is E plus Vm. So where E is equal to 150 plus Vm is equal to 230 into root 2. Therefore, peak inverse voltage will be 475.27 volt. This is a peak inverse voltage. Next, third one, conduction time in millisecond. Conduction time in millisecond. So, can anyone tell me what is the expression for conduction time? Conduction time gamma T is equal to SCR will conduct from alpha to pi minus theta, right? SCR will conduct from alpha to pi minus theta. Therefore, conduction time will be pi minus theta minus alpha. So, pi you have to substitute angle in radian and convert into equivalent at time. So, that will give you a time period of 6.53 millisecond. 6.53 millisecond. And fourth one is a circuit turn off time. So, TC is equal to, for this circuit turn off time is pi plus 2 theta divided by omega in second. Okay. So, let me do one calculation just for you. Pi plus 2 into theta is 27.46. This is in degree. You should convert into radian by multiplying with pi by 180. Denominator omega. What is omega? For 50 Hz source, omega means 2 pi f. This value is 100 pi. So, by substituting this, you will get circuit turn off time is equal to 13.05 millisecond. .05 millisecond. So these are the answers. Okay, I hope it is clear. So far we covered 9 questions. Now let us move to the next one. A single phase 230 volt 50 Hz AC mains fed step down transformer, that is a 4:1, is supplying power to a half wave uncontrolled AC to DC converter used for charging a battery 12 volt DC with the series current limiting resistor being 19.04 ohm. What is the charging current? So it is a single phase half wave uncontrolled, and source side there is a step down transformer. So we can draw the circuit diagram like this. This is a source voltage, and at source side there is a step down transformer, and here uncontrolled rectifier. So device is the diode, load is a RE load. This is a circuit diagram setup. Okay. All right. Now this transformer is 4:1 step down transformer. This transformer is 4:1 step down transformer. Therefore, what is the source voltage at this point? At the secondary of this transformer. So source voltage for this circuit is 230 volt. Therefore, this voltage will be 230 divided by 4 volt. 230 divided by 4 volt. So for the input for rectifier will be Vm is equal to 230 230 by 4 into root 2 volt. Okay. So that is how much it is? 230 divided by 4, 57.5 root 2 volt. Right. Next. What is theta now? Theta is sine inverse E by Vm, where E is equal to 12 volt. 12 divided by 57.5 into root 2. So that is sine inverse 12 divided by 57.5 root 2. 8.486 degree. 8.486 degree. That's all. We got all the calculations. Now you can write down the formula for I naught. What is average charging current drawn by this RE load with the diode circuit? That will be 1 by 2 pi r 2 Vm cos theta minus E into pi minus 2 theta. 1 by 2 pi r 2 Vm cos theta minus E into pi minus 2 theta. So if you substitute these values, it will give you an answer. Average output current will be 1.059 ampere. So the closest answer will be D. The closest answer will be D. Okay. Now let us move further. The circuit in the figure shows a full wave rectifier. What circuit it is? This is the single phase midpoint converter. This is a single phase midpoint converter. The input voltage is 230 volt RMS, single phase AC. The rating of the transformer is 230 volt, 50, 50, 50. That means this winding voltage is 50, this winding voltage is also 50, right? Now the question is, what is the peak voltage across the diode? Peak voltage across the diode. Now, in this case, input voltage to this rectifier, that is the secondary voltage of the transformer. Okay. So, what is Vm for this? Vm for this voltage is 50 into root 2 volt, right? So, the each secondary part of the voltage is 50 into root 2. Therefore, peak inverse voltage for each diode, PIV for each diode is 2 Vm will be 100 into root 2 volt. 100 into root 2 volt. So, 100 into root 2, that is answer A, option A. Okay, answer is option A. Now, in this circuit, I will also give you one question. In my recent video, what we discussed recently, PYQs of 2022-2025, in that also I explained this question, very important. Now, from this question, I will write here, you take this as a practice. Also find RMS voltage rating. RMS voltage rating of each diode. Also find RMS voltage rating of each diode. Okay. So please take that as a practice. All right. Now let us move to the next question. Okay. Now another simple question. I hope you can easily solve it. In the single phase diode bridge rectifier shown in the figure, the load resistance is 50 ohm. The source voltage is 200 sine omega t, where omega is equal to 100 pi radian per second. What is the power dissipated in the load resistor is? Now, in this circuit, first thing you have to calculate what is RMS value of the output voltage. What is RMS value of the output voltage? Single phase full wave rectifier circuit. Okay, so what is RMS value of the output voltage? It is simply Vm by root 2, because you will have output voltage waveform like this. This is a output voltage waveform. This is pi 2 pi, right? So this is a V0 waveform. Therefore, RMS value of that V0 waveform will be Vm by root 2. Now, power delivered to the load, P0 is equal to VOR square divided by R. That's all. You just substitute the values. So, what is Vm by root 2 here? That will give you simply Vm is 200 and root 2 volt. So, substitute this one, 200 square divided by 2 into load resistance is 50. Okay. Therefore, 200 into 200 divided by 2 into 50. So this is 100 times. Here it is a 4 times. So answer is 400 watt. This is a power delivered to the load. Power delivered to the load. Option C is the correct answer for the question. So far I hope it is good. All right, let us move to the next question. This is another very interesting question. A single phase bridge converter is, see, any typical question in gate exam will be something like this. This is a very interesting and conceptual question as well. A single phase bridge converter is used to charge a battery of 200 volts having an internal resistance of 2 ohm as shown in the figure. The SCRs are triggered by a constant DC signal. If SCR2 gets open circuited, means this device got failed, then what will be the average charging current? Now, in bridge rectifier, in single phase bridge rectifier, if any one device, is not working or damaged, then the remaining circuit will simply behave like a single phase half wave rectifier. The remaining circuit will simply operate as a single phase half wave rectifier. Therefore, what is average current drawn by the circuit here? It is simply single phase half wave phase control rectifier with RLE load, with the RE load. So what is the formula for this? 1 by 2 pi R Vm into cos theta plus cos alpha minus E into pi minus theta minus alpha. Okay, so you have to calculate this one. Again, one more thing, SCRs are triggered by constant DC signal. That means alpha is equal to theta. That is why in this question alpha is not given. Okay, why? In a phase control rectifier circuit, you need to give some firing angle, but alpha is given continuously. But conceptually, SCRs don't need firing angle continuously. It need firing angle only for a short period. But whenever firing angle is given continuously, that means whenever SCR is forward biased, the moment SCR is forward biased, immediately it will turn on. Okay, immediately it will turn on. That is why alpha is equal to theta. And what is theta here? Theta is equal to sine inverse E by Vm, where E is 200 volt divided by source voltage 230 into root 2. Okay, 230 into root 2. If I calculate this, sine inverse 200 divided by 230 root 2. This is a 37.94 degree. 37.94 degree. Now, by substituting all of these values, and Vm is 230 root 2. By putting all the values in this 13th question, you will get average output current I0 is equal to 11.9 ampere. You will get 11.9 ampere. So this is the answer for the question. Okay. So we covered so far single phase, half wave and full wave rectifier is going on. The next topic, next circuit. Yeah, this, suppose if you do this problem, it will cover all the calculations for single phase full converter. I really like this question. This question was given in civil services exam as the 20 marks question as well. Okay. So what is, okay, let me read the question first. A single phase fully controlled bridge converter is supplying an inductive load, assuming that the output current is virtually constant and load current is equal to 20 ampere. Determine the following performance measures if the supply voltage is 230 volt and the firing angle is maintained at 30 degree. Find these values. There are 10 questions are given. Let us do it one by one. First question. First question. Better let us go to the next slide. What is average output voltage? Single phase full converter average output voltage formula is 2 Vm by pi cos alpha. Okay, so V naught is equal to 2 into Vm is 230 root 2 230 root 2 by pi. Alpha is 30 degree. Alpha is the 30 degree. Therefore, cos 30 will be root 3 by 2. Then average output voltage equation is, the numerical value is 179.3 volt. Okay. Now, second question. Supply RMS current. What is the RMS value of the supply current in single phase full converter? RMS value of the supply current means RMS value of source current in single phase full converter, that is 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 equal to I naught, that will be 20 ampere. That will be 20 ampere. Now, the third question, supply fundamental RMS current. What do you mean by that? RMS value of fundamental source current. RMS value of fundamental source current. That means IS1 is the question. IS1 is equal to 2 root 2 by pi into I naught. In other words, 0.9 into 20, 18 ampere. And fourth question. Fourth question. Fundamental power factor. Fundamental power factor. So of course, yeah, correct. Source current waveform is a square waveform. So its RMS value will be simply I naught. Its fundamental RMS value will be 2 root 2 by pi into I naught. Correct? Now, fundamental power factor. Fundamental power factor means it is the DPF. Displacement power factor is equal to cos alpha. As alpha is 30 degree, cos alpha will be root 3 by 2 lagging. Root 3 by 2 lagging. Fifth one. Supply power factor. Supply power factor. What is the formula? Supply or input power factor is equal to 2 root 2 by pi into cos alpha. 2 root 2 by pi numerical 0.9. Cos alpha is root 3 by 2. So this fifth numerical is 0.7 lagging. Of course, there is some other numbers also. 0.9 into root 3 by 2. 0.78. 0.78 lagging. Okay, next. Sixth calculation. Sixth one is supply harmonic factor. It is simply nothing but percentage of THD in source current. This is a very standard number. Okay, 48.43%. is percentage THD for any square wave. You can also say this is for any square waveform. Percentage THD is 48.43% for any square waveform. Next, seventh one, RMS value of the output voltage. RMS value of output voltage. So for single phase full converter, RMS value of the output voltage is simply Vm by root 2. Okay, so that will give you simply Vs. So this is equal to 230 volt. That is a 230 volt. Next, eighth calculation, voltage ripple factor. Voltage ripple factor, let me write VRF. This is square of the RMS voltage minus square of the average voltage under root divided by average voltage into 100. Now if you substitute, VOR is equal to 230, V0 is equal to 179.3, and if you substitute in this, you will get this answer is 80.3%. This answer is the 80.3%. Okay. Next, ninth one. So this ninth one is very important. Active power input, reactive power input. Remember, in single phase full converter, single phase semi converter, or three phase full converter, three phase semi converter, in all these circuits, source voltage is pure sinusoidal, but source current is not sinusoidal. Therefore, we should express these values in terms of fundamental components. Okay, so with that statement, active input power is equal to Vs1 Is1 into cos phi 1, where Vs1 is RMS value of fundamental source voltage, that is simply same as 230. Is1 is RMS value of fundamental source current 2 root 2 by pi into I0, where I0 is 20, into cos alpha, where alpha is equal to 30 degree. So if you substitute these values, you will get 3585.3 in watt. 3585.83 in watt. Similarly, reactive power input to the circuit, that is Q in, is equal to Vs1 Is1 into sin phi 1, right? So again 230 into 2 root 2 by pi into I0. This is Is, of course. Is is nothing but I0 is nothing but 20. Let us substitute that directly. This is 20 into sin 30 degree. What is phi 1 here? That is phase angle between fundamental source voltage and fundamental source current. This numerical value will come around 2070. 2070 VAR. Okay. So this question, the purposefully I selected this question because it will cover all calculations. Okay, it will cover all calculations. So in single phase full converter, what are the important things? Average output voltage, source current, RMS value of fundamental source current, displacement power factor, which is also called fundamental input power factor, and input power factor, and percentage THD in source current, input power and input active power, and input reactive power, right? So with this I thought we can cover all these calculations. Next, Again, this is another favorite question to me, right? Even there are 4-5 questions on this model. This is very important. This model is this is a very important question. So not only from power electronics, this question is important from this question is important from measurements also. Now, what is the main thing here? The input voltage to the converter is 100 root 2 sine of 100 pi t volt. Current drawn by the converter, some equation is given. By seeing this equation, we can understand that current drawn by the converter is not pure sinusoidal. That is the general case. It has fundamental third harmonic and fifth harmonic components. By observing this omega numbers, you can get that conclusion. Fundamental is 100 pi, third harmonic 300 pi, fifth harmonic is 500 pi. What is the input power factor and what is active power drawn by the converter? So first let us do active power drawn by the converter. That is, just now I told, if the current is non-sinusoidal, you should consider fundamental components. You should consider fundamental components. That means V1 I1 into cos phi 1. Okay. What is V1? RMS value of the fundamental voltage. That will be 100, or else you can take one more step, 100 root 2 divided by root 2, and RMS value of the fundamental current, 10 root 2 divided by root 2 into cos phi 1, cos pi by 3. Okay. So cos pi by 3 is 1 by 2. So root 2 cancel. So this will give you 500 watt. This will give you 500 watt. Okay. Next, what is the input power factor? When source current is or current drawn by the converter is not pure sinusoidal, you should find out the power factor based on a formula like this. IPF is equal to distortion factor multiplied with displacement power factor. So you have to calculate this one by one. What is DPF? DPF is equal to cos of phase angle between fundamental voltage and fundamental current, that is pi by 3. So this will give you 1 by 2. DPF is equal to cos pi by 3, that value is equal to 1 by 2. And what about DF? Distortion factor is equal to I1 divided by I, where I1 is nothing but RMS value of the fundamental current, 10 root 2 divided by root 2. Denominator, square root of RMS value of the current, square root of individual components, 10 root 2 divided by root 2 whole square plus 5 root 2 divided by root 2 whole square plus 2 root 2 divided by root 2 whole square. Okay. So if you simplify this, it will give you 0.88. Therefore, input power factor will be distortion factor is 0.88 into displacement power factor is 1 by 2. This will give you 0.44 lagging. This question is very, very important. Same question 2 to 3 times it is repeated. Again, we can expect the model can repeat in a upcoming GATE exam as well. All right. Now, Okay, now see this question. This is a very recent question. In 2024 it is given. So we'll take a short break after this question. Let us finish this one. Before this question, I would like to clarify one thing. This question is based on the drives concept, but still this question is given in GATE exam. Drives is not there, but this is given as just based on. No. There is one question, sir. Can we use active power divided by VSIS? So yeah, even you will get the same answer. That also you can use it. Now, single phase fully controlled thyristor converter bridge is used for regenerative braking of a separate leg set DC motor with the following specifications. Rated armature voltage of the motor is 210 volt. Rated armature current is 10 ampere. Rated speed is 1200 rpm. Armature resistance is 1 ohm. Input to the converter bridge is 240 volt at 50 hertz. The armature of the DC motor is fed from the fully controlled bridge and the field current is kept constant. Assume that the motor is running at 600 rpm and the armature terminals of the motor are suitably reversed for regenerative braking. If the armature current of the motor is to be maintained at the rated value, the triggering angle of the converter is. So finally, in a simple terms, a DC motor is operating in a regenerative braking. So you have to find out how much terminal voltage required for that. So for that, first let us calculate at rated conditions at rated conditions, let us find back EMF and also let us call it EB1, terminal voltage minus armature resistance drop. So that will give you what is terminal voltage of the DC motor, that is the 210. 210 minus 10 into 1. Therefore, at rated conditions, back EMF voltage is the 200 volt. Rated conditions means at a speed of 1200 rpm. Okay, so this is the back EMF at 1200 rpm. Now the motor is going to regenerative braking at 600 rpm, at a 600 rpm. Okay, therefore what you have to do here, at 600 rpm, at 600 rpm, back EMF EB2 can be, because back EMF is proportional to speed, this will be 100 volt. Okay, this will be 100 volt. Therefore, under this condition, during regenerative braking, terminal voltage is equal to, now you have to change back EMF polarity in the braking condition, plus you cannot change a current direction. Therefore, this voltage is equal to minus 90 volt. So, in order to operate the DC motor in the regenerative braking, how much terminal voltage required for this? We need minus 90 volt. This minus 90 volt, who will supply? This will be supplied by single phase full converter. So, single phase full converter output voltage 2 Vm by pi cos alpha should be equated to minus 90. With this equation, you have to find alpha value. Therefore, cos alpha is equal to minus 90 into pi divided by 2 into Vm, where Vm is 240 root 2. 240 root 2. So, from this, you will get alpha value is equal to 114 615 degree. 114 615 degree. Okay, so this is the required firing angle that you can get it. All right, now let us take a short break. Let us take 15 minutes break. We'll come back shortly. Now time is 11:45 now. We'll come back at 12 p.m. We'll come back at 12 noon, right? Okay. We'll restore the class at 12 noon. Okay, students, welcome back. Now, is the screen everything visible? My audio, video, or everything is fine? Please comment. Okay, now let us move forward. Question number 17. For an ideal AC to DC rectifier circuit shown in the figure below, the load current magnitude of IDC is equal to 15 ampere. That means the load current is constant. The thyristors are fired with a delay angle of 45 degree. What is the amplitude of the fundamental component of source current? Now, in this case, what is the given circuit diagram? The given circuit is, this is the single phase semi converter. The given circuit is single phase semi converter. In this circuit, source current is a quasi square waveform. Quasi square waveform. Now, what is the question here? What is the amplitude of fundamental component of that quasi square? So that I can write it like this: IS1 peak. Even at the beginning of the video, we discussed one problem about quasi square waveform is equal to 4I0 or IDC divided by pi into cos alpha by 2. 4I0 by pi into cos alpha by 2. So, where I0 or IDC is equal to 15 divided by pi into cos alpha by 2, where alpha is equal to 45 degree divided by 2. So, this numerical value is 17.64 ampere. The numerical value is 17.64 ampere. Okay. So this question is based on semi converter and source current waveform shape. Now let us move to the next question. So if you understand the flow by using some PYQs, I'm covering each and every topic. And in YouTube, in our Home Institute YouTube channel, there is one more video from my side. Complete notes I shared in the video and I explained it. It is around 3 to 3.5 hours video. If you go through that video and this one, completely set everything for power electronics for your gate preparation. Now the next question, a phase controlled, half controlled single phase converter is shown in the figure. The firing angle is 30 degree, source voltage 230 volt RMS. If the load current is 10 ampere, then find the power delivered to the load. So I can write here power delivered to the load will be V0 into I0. V0 into I0. For again, this is also single phase semi converter with the symmetric configuration. What is V0? Average output voltage formula. Vm by pi into 1 plus cos alpha multiplied with I0. Therefore, if you substitute the numericals, Vm is 230 into root 2 divided by pi into 1 plus cos alpha is 30 degree into I0 is 10. Now, this numerical, it will be 1932 in watt. 1932 in watt. So that is the power delivered to the load. So single phase semi converter, we have seen two problems. One is based on source current formula, another is based on V0 and I0 expressions. Now let us move to the next question. Yeah, this question is based on source inductance concept. Before that, let me write down some basic equations. Single phase full converter with source inductance. Single phase full converter with source inductance. There are three important equations that you need to practice. One is average output voltage. V naught is equal to 2 Vm by pi cos alpha minus 2 omega ls by pi into I naught. So the second term in this equation is average voltage reduction due to source inductance in single phase full converter. And the second expression that is important is I naught is equal to Vm by pi into cos alpha minus cos of alpha plus mu. Cos alpha minus cos of alpha plus mu. And one more equation will be cos of alpha plus mu is equal to cos alpha minus 2 omega ls divided by Vm into I naught. Now if you see in the first equation and third equation, second term, first equation denominator is pi, third equation denominator is the Vm. So with ls during overlap interval, all all four thyristors in single phase full converter will conduct. It's a very, very important thing. Will conduct. And in this circuit, displacement power factor is equal to cos of alpha plus mu by 2. These are the important formulas that you should practice. Okay, these are important concepts that you have to practice under the topic single phase full converter with source inductance into account. Now on this concept, there is one PYQ. Let us look into that. Single phase full bridge fully controlled thyristor rectifier feeds a load comprising of 10 ohm resistance in series with a very large inductance. The rectifier is fed from an ideal 230 volt 50 hertz sinusoidal source through cables which have negligible internal resistance and a total inductance of 2.28 millihenry. That means source side inductance of 2.28 millihenry. If the thyristors are triggered at alpha is equal to 45 degree, alpha is equal to 45 degree, the commutation overlap angle in degree will be. Okay, so let us see this one. So finally you have to find what is overlap angle. In order to find overlap angle, you should take this equation. In this equation, you need I naught. So before substituting in that equation, you have to solve I naught value. So what is I naught here? V naught. Let us find out. 2 Vm by pi cos alpha minus 2 omega ls by pi into I naught. 2 omega ls by pi into I naught. Okay. So what is V naught here? I naught into R. So let us substitute that. So I naught is unknown. I naught into what is the load resistance? Load resistance of 10 ohm. So I naught into 10 is equated with 2 Vm by pi cos alpha. 2 into source voltage is 230. Therefore, Vm will be 230 into root 2 divided by pi into cos alpha, where alpha is equal to 45 degree. So cos alpha will be 1 by root 2 minus 2 into, as the frequency is 50 hertz, omega will be 100 pi divided by pi. Source inductance is 2.28 millihenry. So 2.28 divided by 1000 into I naught. Okay, into I naught. So by solving this equation, you will get I naught is equal to, I naught is equal to 14 ampere. You will get I naught is equal to 14 ampere. Once you have I naught value, then you can find overlap angle by substituting this formula. Cos of alpha plus mu is equal to cos alpha minus 2 omega ls by Vm into I naught. Okay. So I hope you can substitute the data. Again, almost all similar data. By solving this, you will get overlap angle is equal to 4.81 degree. Overlap angle is equal to 4.81 degree. Okay. Right. Now let us move to next question, next concept. This is also based on single phase full converter with source inductance only. The figure below shows an uncontrolled diode bridge. What do you mean by, what is the difference between thyristor bridge and diode bridge? That is with the alpha is equal to 0. You can consider this as the SCR bridge with alpha is equal to 0 degree. You can consider this as an SCR bridge with the alpha is equal to 0 degree. Okay. Now, what is the question? The load draws a constant current of 14 ampere. The conduction angle of the diode D1 in degree. Okay. Suppose if source, if it is a source inductance is not given, in that case, the source current waveform will be simply plain square waveform. Simply plain square waveform. When the source inductance is given, then what happens? Instead of sudden change, it will have this gradual change, right? So this waveform will be something like this. It is a square waveform. Therefore, each device or each diode, each device conducts for 180 degree plus that overlap interval. Therefore, first you have to calculate overlap interval. Cos alpha plus mu. Let us write a basic formula is equal to cos alpha minus 2 omega ls divided by Vm into I naught. So from this, alpha is equal to 0. Therefore, cos mu is equal to, as alpha is equal to 0, cos alpha will be 1 minus 2 into frequency 50 hertz. Therefore, omega will be 100 pi. Inductance will be 10 millihenry. So I can write 10 divided by 1000 into Vm 220 into root 2 I naught 14 ampere. So from this you will get overlap angle. Overlap angle will be 44 and conduction angle for diode will be 180 plus this 44, it will give you 224 degree. Okay, will give you 224 degree. So that will be the answer. Now this one, this is also just see these two questions 20 and 21, both the questions given in the same year. Okay, see this is a 2017 set 1 and this is 2017 set 2. Now here same concept. In the circuit shown, the diodes are ideal, the inductance is small and the load current is finite value which is constant. Which one of the following statements is true? Now say for example, if this source inductance is not there, in that case D1 will conduct from 0 to pi. Okay, this is 0 to pi, and D2 will conduct from pi to 2 pi. Okay, this is a D2 and this is a D1, right? Now because of the source inductance, what happened, this current suddenly instead of coming from I0 to 0, it will slowly come down. That means each diode conducts for more than 180 degree. Each diode conducts for more than 180 degree. D1 conducts for greater than 180 degree. D2 will also conduct for greater than 180 degree. Okay, so option A will be the correct answer for this question. Now let us move to the next question. I think with that I can conclude single phase rectifiers. Now let us move to the second part of chapter 2, that is the three phase rectifiers. That is the three phase rectifiers. Now in three phase rectifiers, only thing you have to look into is three phase half wave rectifier, three phase half wave rectifier, both based on diode as well as SCR. With SCR, it is referred as a phase control rectifier. And another circuit that you have to look is three phase full wave rectifier. Three phase full wave rectifier. In three phase full wave rectifier, the two important circuits are three phase full converter and three phase semi converter. Three phase full converter and three phase the semi converter. Okay, now let us look into the questions one by one. Now it's a very simple circuit. It is based on three phase half wave diode rectifier. The circuit shown in the figure is a three phase half wave rectifier. The source is a symmetrical three phase four wire system. The line to line voltage of the source is 100 volt. Supply frequency is 400 hertz. So input frequency here is 400 hertz. Now what is the ripple frequency of the output? So ripple frequency, how to define it? It is based on number of pulses in the output voltage of the rectifier circuit. So I can say that three phase half wave rectifier circuit output voltage contains 3 pulses. Output voltage contains 3 pulses. Therefore, ripple frequency is equal to N into F in. That will be where N is equal to number of pulses in the output voltage by the time source voltage completes one cycle. That is 3 into 400 will give you 1200 hertz. 1200 hertz. So answer will be option C. Now let us move to the next question. Now here this circuit is based on, this question is based on a 3-phase half-wave controlled rectifier is operating from a 3-phase star connected supply of 220 volt 50 hertz. Okay, so if nothing is specified, the given voltage you can consider that RMS value of the line voltage, that will be 220 volt. As the question is based on 3-phase half-wave circuit, we need VMP. So VML is equal to 220 root 2 volt. From that, VMP is equal to VML divided by root 3 volt. VML divided by root 3 volt. The load resistance at the DC terminals of the rectifier is a 10 ohm at 75% of the maximum DC output voltage. This is a very important, the crux of the question is that statement only. Okay, at 75% of maximum DC output voltage. What do you mean by that? In 3-phase half-wave rectifier circuit, if V0 is greater than 86.6% of 86.6% of VO max, 86.6% of VO max. That means the circuit will be operated in continuous conduction. Continuous conduction. Okay, 3-phase circuits don't scare about it. If you prepare in a proper structured manner the important concepts, it's very easy. Why? Because 3-phase circuits, as everyone feel difficulty, the questions will be simple questions. Okay, in my opinion, 3-phase from the examination point of view, you can answer very easily. Just 4 or 5 formulas if you remember perfectly. If V0 is less than 86.6% of VO max, then it will be discontinuous conduction. It will be discontinuous conduction. Okay, right. So under this condition we have to find it out. Therefore, what is given here? At 75%, 75% means it will be treated as a less than 86.6% of the output voltage. Therefore, the given condition is a discontinuous conduction. So it is given is in DCM, discontinuous conduction mode. Average output voltage equation will be 3 VMP divided by 2 pi into 1 plus cos of alpha plus pi by 6 is equal to 3 by 4 times VO max. What is VO max? VO max is equal to 3 VMP divided by divided by 2 pi into root 3. Basically 3 root 3 by 2 pi into VMP into cos alpha. When you substitute alpha is equal to 0, you will get that. Now let us substitute here. 3 VMP. What is VMP? 220 root 2 divided by root 3. Denominator 2 pi into root 3. So from this, by solving this equation, you will get alpha is equal to 42.6 degree. This is one of the important model in three-phase topic. Simple one, but it is not a straightforward question. Okay, 42.6 degree. Next, average output current. Second part of the question, average load current. I naught is equal to V naught by R. What is V naught? 3 by 4 times VO max. What is VO max? 3 root 3 by 2 pi into VMP, where VMP is equal to 220 root 3 220 into root 2 divided by root 3. Total divided by load resistance. Load resistance is 10 ohm. So 1 by 10. By calculating that, you will get 11.4 ampere. This is the average output voltage. So there is a one question. Can you also discuss the range of angle which the single phase bridge rectifier behaves as an inverter? That was already covered. That is the, of course, I have not used that concept. Okay, anyhow, as the question is asked, this is based on this question is based on regenerative braking. That means when alpha is greater than 90 degree, single phase full converter will operate as the inverter only. So if you see here, we got alpha value greater than 90 degree. If you want, I will write down the conclusions. A good question. Single phase full converter. Yeah, this particular quadrant diagram you will understand easily. This is I naught and this will be V naught. Okay. So when alpha is less than 90 degree, both V naught and I naught are positive. In that circuit, in that condition, circuit will be operating as a rectifier. When alpha is greater than 90 degree, output voltage is negative. In that case, circuit will operate as an inverter. If the load is a DC motor, first quadrant of operation will be treated as forward motoring. When alpha greater than 90 degree, that will be reverse regenerative braking. So this question is based on reverse regenerative braking, and that is why we got alpha value greater than 90 degree. Anyhow, thank you for asking the question. So that is the spirit. If you have any specific thing in your mind, please let me know. So let us continue our discussion. Yeah, we are, I hope this problem is clear. This is a three-phase half wave phase control rectifier. Only while solving this problem, you have to check these two lines of conditions. When V naught is less than 86.6% or more than that. If it is less than, you have to apply continuous conduction formula. In continuous conduction, what is the equation? That is 3 root 3 by 2 pi into VMP into cos alpha. Okay. All right. Let us move to the next topic. Now, a three-phase diode bridge is fed from 400 volt RMS 50 hertz three-phase AC source. If the load is purely resistive, what is the peak instantaneous output voltage? So this is also, if you have a small understanding on waveform, this question is very simple. Three-phase diode bridge. Three-phase diode bridge means you will have output voltage like this. Total you will have, there are 6 pulses. 6. Okay. This is the output voltage waveform. Now, what is the question here? What is the peak instantaneous output voltage? So, what is this peak value? This peak value is simply nothing but VML only. Peak value of the line voltage. So, for the previous question, there is a one question in the chat window. Okay, I will come to that. Let us finish this one. I understand what you are asking. I will answer it. Now, in this case, what is the peak instantaneous output voltage? That is simply VML. Okay. VO peak is equal to VML. What is VML? Source voltage is given as 400 volt. So 400 into root 2 volt. 400 into root 2 volt. That is the output voltage. Peak instantaneous value of the output voltage. I hope this is clear. Now, students, listen. There is a one question in the chat window. In the previous question, if it is a continuous conduction mode, what is the expression for average output voltage? Very good question. Now see here, in this case, we said this is a formula for discontinuous conduction mode. Suppose if it is a continuous conduction, in case of continuous conduction mode, CCM, expression for average output voltage is 3 root 3 divided by 2 pi VMP into cos alpha. This is the formula. Okay. At least in three-phase rectifier, don't worry about RMS voltages. You just focus on average output voltages. Therefore, in this circuit, for continuous conduction, 3 root 3 by 2 pi VMP cos alpha. For discontinuous conduction, 3 VMP divided by 2 pi into 1 plus cos of alpha plus pi by 6. Okay. Now see here, there is no root 3 in discontinuous conduction. Why it is not VMP? It is VMP only. This is VMP. This is VMP. Pujari Rajkumar, why it is not VMP? You are asking this question. Can you please mention the question number? Are you referring 23 or 24? I hope you are referring 24, if I am not wrong. In this case, you are referring, right? That is, so this is VML. Why? Because in case of three-phase diode bridge, correct. Three-phase diode bridge, what is the main concept? Say, for example, if I go back, this is the circuit diagram. This is the load. So this is the source voltage. Now say this is A, B, C. Let us take load terminals X and Y. Okay. Now listen carefully. What is that name? Pujari Rajkumar. For your question, answer. Suppose at any point of time in three-phase bridge rectifier, at any point of time, two diodes will be in conduction. Either two diodes or two thyristors. One device is from upper half, another device is from lower half. Now, say for example, these two devices are in conduction, right? In that case, what is output voltage? Output voltage will be X is connected to A, Y is connected to C. That means output voltage will be VAC. So in that way, at every instant of time, at every instant of omega t, two devices, one device from upper half, another device from lower half will be in conduction. So output voltage is subjected to any one line voltage, any one line voltage. With that extension, this question is framed. What is the peak instantaneous value of the output voltage? As the load is connected to any line voltage at any point of time, because of two diodes are in conduction, output voltage peak value will be peak instantaneous value of the line voltage, not a phase voltage. Suppose if the same question from three-phase half-wave rectifier, in that case, the peak instantaneous output voltage is equal to VMP. It's not a VML. Okay. I hope that is clear. That is why here we are taking VML as an answer, right? Sorry. Now let us go to the next question. A fully controlled, naturally commutated three-phase bridge rectifier is operating with a firing angle of 30°. The peak-to-peak voltage ripple expressed as the ratio of the output voltage of the converter circuit. Again, for this circuit also, you can take the previous waveform. Peak-to-peak ripple. What do you mean by peak-to-peak ripple? That means this difference. This difference is a peak-to-peak ripple. Delta V naught I can take. Delta V naught. Now, in this circuit, as the alpha is given as a 30°, VML sin omega t, sin 30 will be 1/2. Diode RMS current, we are going to have one question. Don't worry, I will cover that. So, delta V naught will be, now here, delta V naught is equal to VML minus VML by 2. Okay, VML minus VML by 2. The main reason is here, this is the pulse. I'm just focusing on one pulse. Okay, so if you see here, this peak value is VML, and because of 30°, this value is VML by 2. VML by 2. Therefore, delta V naught will be VML minus VML by 2. So, what is that? That is equal to VML by 2. Now, the question is, the peak-to-peak ripple expressed as the ratio of peak value of the output voltage. That means, peak value of the output voltage will be VML. So, what is the ratio between delta V naught and VML? Okay, delta V naught, we got it VML by 2, denominator VML. This answer will be 1/2. This answer will be 1/2. That is 0.5 will be the correct answer for this question. Now, next question. A 6-pulse thyristor rectifier bridge is connected to a balanced 50 Hz 3-phase source. Assuming that the DC output of the rectifier is constant, the lowest frequency harmonic component in the AC source current is. Now, remember here, input current in three-phase full converter is quasi-square waveform. Quasi-square waveform. This is very important question. And IS contains 6k plus or minus 1 harmonics only. 6k plus or minus 1 harmonics only. Triple N harmonics are absent. Triple N harmonics are absent. Therefore, if only 6k plus or minus 1 harmonics, what are that numbers? That means IS contains 5, 7. If k is equal to 1, 6 minus 1 will be 5, 6 plus 1 will be 7. If k is equal to 2, 12 minus 1, 11. If k is equal to 2, 12 plus 1, 13, and so on. Therefore, in this sequence of the numbers, lower order harmonic is the fifth harmonic. Lower order harmonic is fifth harmonic. Therefore, input frequency is 50 hertz. Lower order harmonic is the fifth harmonic. Hence, the frequency of the lower order harmonic will be 5 into 50, 250 hertz. Option C will be the correct answer. Next question. Yeah, now someone asked how to find RMS value of the diode. Now this question will address that. A three-phase diode bridge rectifier is feeding a constant DC current of 100 ampere. Okay, that means I naught is equal to 100 ampere to a highly inductive load. That means load current is constant. If three-phase 415, 50 hertz AC source is supplying to this bridge rectifier, what is the RMS value of the current in each diode? So, if you draw a diode current waveform in a one cycle of 360 degree, you can take any one diode, let us say generally diode. Diode will conduct for a period of 120 degree or 2 pi by 3. So, diode conduction will be for 2 pi by 3 in a cycle of 2 pi. One cycle is 2 pi, means 1/3 of the cycle diode is conducting. Next cycle, again the current waveform will repeat like this. So, this magnitude is I naught. Therefore, how to find RMS value for this waveform? IDRMS, it is a rectangular waveform. Magnitude square into function duration divided by cycle time. You have to take a root for that. That will give you I naught divided by root 3 ampere. This is very important. That's why there is a doubt in the chat window. Again, I have also covered this in my slides. So, where I naught is equal to 100. So, I naught divided by root 3. Therefore, RMS value of the diode current will be 57.7 ampere. Okay. Now, let us go to the next question. Yeah, this is another important and interesting question. A solar cell of 350 volt is feeding power to an AC supply of 440 volt, 50 hertz through a three-phase fully controlled bridge converter. Now, understand, solar cell power flow direction is from solar cell, means DC side to AC side. Therefore, in this circuit, the bridge rectifier will operate as an inverter. Okay, so let me write down here. Power flow
is from DC to AC. That means the given bridge will operate as an inverter. That means the given bridge will operate as an inverter. Therefore, how to write output voltage equation? I naught into R, you should change the polarity of the DC side voltage. I naught into R minus E. Now, if the solar cell resistance is given, each thyristor will be reverse biased for a period of. So that conclusion will be, you can get that conclusion based on the firing angle. First, you should examine what is the firing angle. So before that, first let us calculate this value. I naught is given 20 into solar cell resistance is given 0.5 minus solar cell voltage is given 350. So 10 minus 350 minus 340 volt. This is the output voltage. Who should supply this voltage? Three-phase full converter. Three-phase full converter output voltage will be 3 VML by pi into cos alpha is equal to minus 340. Minus 340. Therefore, from this you can solve the value of alpha. Cos alpha is equal to minus 340 into pi divided by 3 into VML. What is VML here? 440 into root 2. 440 into root 2. Okay. So from this you will get alpha value is equal to 125 degree. Now in this case, in this question, we need to find out how much time each thyristor will be reverse biased. So here, if alpha is less than 90 degree, if alpha is less than 90 degree, then each SCR reverse biased for 4 pi by 3 minus alpha. Each SCR is reverse biased for a period of 4 pi by 3 minus alpha. If alpha is greater than 90 degree, then each SCR is reverse biased for pi minus alpha. We got the condition alpha is greater than 90 degree because of inverter operation, and that alpha is the 125 degree. Therefore, for this question, each SCR will be reverse biased for a period of 180 minus 125. That will give you 55 degree. That will give you 55 degree. Okay. So I hope this is clear. Now let us move to the next question. A three-phase fully controlled bridge converter with freewheeling diode is fed from 400 volt 50 Hz AC source and is operating at a firing angle of 60 degree. The load current is assumed to be constant at 10 ampere due to high load inductance. The input displacement factor and the input power factor of the converter will be. Okay. So input displacement factor. What do you mean by that? That is simply nothing but DPF, input displacement factor. In this question, it is mentioned as a IDF, that is equal to cos alpha. As alpha is given 60 degree, this is 1 by 2 or 0.5. Input displacement factor is 0.5. What is the next question? And input power factor IPF is equal to, in three-phase full converter, IPF formula is 3 by pi into cos alpha, where 3 by pi is nothing but 0.955 into 1 by 2. This value will be 0.478. Input power factor is always lagging for any rectifier circuit because of the source current harmonics. Due to source current harmonics, it is always lagging. So option C will be the correct answer for this question. Next question. I'm sorry, same question is repeated. Please ignore this. Ignore, because this question is repeated. I'm sorry, it is my bad. Now, let us look into the 31. A three-phase fully controlled bridge converter is feeding a load drawing a constant and ripple-free load current of 10 ampere at an alpha 30 degree. The approximate total harmonic distortion and RMS value of the fundamental component of input current. So in three-phase full converter, first let us find out RMS value of fundamental load current, fundamental input current. That is root 6 by pi into I naught. I hope you are referring your revision notes. So this session is not to derive all these formulas. So these formulas also I explained, whatever video I mentioned at the beginning. Please go through that video. Even in this video also we'll give that a description link. Please go through that. So load current is 10 ampere is given. Therefore, this will be 0.78 into 10. This will be 7.8 ampere. 7.8 ampere. Next, RMS value of the source current I naught into root of 2 by 3. So this will be 10 into 0.816. That means 8.16 ampere. These are the RMS value of the source current. Now, percentage THD. Percentage THD in IS is equal to IS square minus IS1 square under root divided by IS1 into 100. By substituting those numbers, you will get 31.1%. So, what are the answers? Option B will be suitable for this question. 31% and 7.8 ampere. RMS value of fundamental source current will be 7.8 ampere. Okay. Now let us move to the next question. A fully controlled three-phase bridge converter is working from 415 volt. So this is the 415 volt, 50 hertz AC supply. It is supplying a constant current of 100 ampere at 400 volt to a DC load. Assume large inductive smoothing and neglect to overlap. The RMS value of AC line current in ampere. Just now we have calculated RMS value of AC line current. That means RMS value of the source current I naught into root of 2 by 3. What is I naught given? 100. 100 into root of 2 by 3. This value is 81.16 ampere. 81.16 ampere. Okay. So I just selected three-phase questions in such a way that in order to encourage you, don't scare about three-phase circuits and don't neglect also. What I observed, students used to scare three-phase rectifiers and simply in the exam, whenever three-phase rectifier word is given, simply they will ignore. It is not in my bucket. But sometimes very simple questions will be given in the exam. Okay, don't skip it. At least while watching today's video, the value addition will be, if you have that fear, just remove that fear. At least practice what questions I solved in this video. Okay, any similar model repeated in your gate exam, there is definitely a value addition for your today's efforts. Okay, let us go to the next video. Sorry, next question. I hope with this we covered three-phase rectifiers, and this slide will tell you we are going to start one online live course on February 2nd, and the features you can see. If you want to, if you are interested for upcoming batches, you can contact this number 95156 94053. So you will get all the details about it. So I will take live sessions. So at your comfort of your home, you can watch these uh, all subjects. Okay, of course I will cover power electronics in that. All right, now let us move to the next topic, that is DC to DC converters. So this is a very simple chapter, very conceptual, and definitely suppose if you get 5 questions from power electronics, you can expect 2 questions from this chapter, DC to DC converter, or you can also say choppers. There are 3 basic circuits. Okay, one is the, in this chapter you have to look into 3 circuits. One is buck converter, or you can also say step down, right? The second circuit is boost converter, this will be step down, I'm sorry, step up. Third one is buck boost converter. Buck boost converter. This will be step down up chopper. Right, step down up chopper. Anyhow, I will not redraw the circuit diagrams. In the next slides you will see the circuits. Apart from this, you should also look into, focus into commutation circuits. Commutation circuits, you just need to focus 2 schemes. One is current commutation, and second one is voltage commutation. Second one is the voltage commutation. Complementary commutation, nowadays you are not getting any question. We got one question, only one question in entire gate history. In 2006 there was a question. After that there are no questions. Only focus on these topics. Okay, now let us move to the question. Now see here, this question is based on, see, in this particular chapter, first thing before starting any questions, I will suggest you to draw circuit diagram for all the 3 circuits, right? What are that? Buck converter, this circuit is for buck converter, like that boost converter and buck boost converter. So first you have these 3 circuit diagrams readily available with you. Okay, after that you can start practicing any questions, right? Now this is a buck converter question. Now let us read the question. A buck converter as shown in the figure A is working under steady state. Most of the times you will get a questions, the circuits are operating in a steady state. Okay, the output voltage and the inductor current can be assumed to be ripple free. Now figure B shows the inductor voltage VL during a complete switching interval. Assume all the devices are ideal. What is the duty cycle ratio of this buck converter? Now remember, whether it is a buck converter, boost converter, or buck boost converter, the idea is steady state is nothing but volt second balance will satisfy. Okay, that means if you have inductor voltage waveform, net area under VL waveform will be 0 for one cycle. Therefore, I can write it like this. In steady state, in steady state, net area under VL waveform is equal to 0. Okay, that is nothing but volt second balance. That is nothing but volt second balance. So if you take what is net area under the waveform here, 30 into turn on time. 30 into turn on time means dt. This will be equal with 20 into turn off time. That means 1 minus d into t. That's all. If you equate and just rearranging the terms here and there, you will get the answer. You can cancel t on both sides. Therefore, you will get 3 by 2 is equal to 1 minus d divided by d. So, 3d is equal to 2 minus 2d. Therefore, 5d is equal to 2. D is equal to 2 by 5, whose numerical value is 0.4. So, answer for this question, the duty cycle ratio of this buck converter will be 0.4. Okay. Now, just please do this question. I will come in 1 minute. So, answer for this question is 0.4 duty cycle ratio. Now, let us move to the next question. Again, a question on buck converter. This figure shows the circuit diagram of a chopper or buck converter. The switch S in the circuit in figure 1 is switched such that voltage across this diode is given. Okay. The capacitance is so large so that the voltage across it is constant. Switch S and diode are ideal. Now the question is, what is the peak to peak ripple in inductor? Peak to peak ripple in inductor. Okay. All right. Now, this is a buck converter circuit. Therefore, peak to peak ripple in inductor current, let me call it delta IL. In buck converter, delta IL formula will be VDC by L d into 1 minus d into t. So, you need to find a d value for this. From this waveform, turn on time is 0.05 and total cycle time is 0.1 millisecond. Therefore, here I can say that d is equal to 1 by 2. Correct? Total cycle time is 0.1, half of that is 0.05. So, duty cycle ratio is 1 by 2. Now, substitute the data. Source voltage is 100 volt divided by inductance 1 millihenry 10 power minus 3 into 1 by 2 into 1 by 2. Total cycle time is 0.1 millisecond into 10 power minus 3. Okay. Now, the answer will be 25 ampere. Peak to peak ripple in inductor current will be 25 ampere. Now the next question. A buck converter feeding a variable resistance as shown in the figure. The switching frequency of the switch is 100 kilohertz and the duty ratio is a 0.6. Let me note down the data here. Switching frequency is a 100 kilohertz. Therefore, one cycle time will be 10 microsecond. Duty cycle ratio is given as a 0.6. Output voltage V0 is equal to 36 volt. V0 is equal to 36 volt. Input voltage VDC is equal to 60 volt. Okay. Assume that all the components are ideal and that the output voltage is ripple free. The value of R in ohm, that will make the inductor current just continuous. Inductor current is the just continuous. That means it is given as boundary condition. It is given as the boundary condition. So at boundary condition, at boundary condition, what is the equation here? Okay, at boundary condition, 2L divided by RT is equal to 1 minus D. If you just know this equation, you can easily find out. So in this condition, you have to find what is the R value. Therefore, 2 into inductance value is 5 millihenry divided by load resistance into cycle time is 10 microsecond is equal to 1 minus 0.6. By solving this equation, you will get R is equal to 2500 in ohm. You will get this resistance is equal to 2500 in ohm. Okay. Answer for the question is 2500 ohm. Next. Yeah, this statement is very lengthy for this question. Circuit diagram also a little bit scary, but very simple question. Let me read it. The figure shown two buck converters connected in parallel. The common input DC voltage for the converters has a value of 100 volts. The converters have inductors of identical value. The load resistance is 1 ohm. The capacitor voltage has negligible ripple. Both converters operate in the continuous mode. The switching frequency is 1 kilohertz and the switching control signals are shown in the figure. So by seeing this, duty cycle ratio is a 0.5. See, total cycle time is 1 millisecond and each switch is operating as a 50% duty cycle ratio. Now the question is, the circuit operates in steady state assuming that converters share the load current equally. This is an important statement. Converters share the load current equally. Okay, that is an important statement. What is the average value of this one? Switch current, ISW1. Okay, this is a ISW1. What is the average value of the switch current? That is the question. Now, first thing, for the two buck converters, input voltage is common. Of course, both are connected in a parallel at the load side. Therefore, parallel side output voltage is also same. So, what will be average output voltage for this circuit? D into VDC. D is equal to 0.5. Source voltage is 100. Therefore, it will give you 50 volts. So, average output voltage V0 is equal to 50 volt. That is the first point. Therefore, what is I0 here? Average output current? I0 will be 50 ampere. Load resistance is 1 ohm. So, I0 will be 50 ampere. two inductors are identical and both are sharing current equally. What do you mean by that? First inductor current is 25 ampere. Second inductor current will be 25 ampere. Therefore, both will supply load current of 25 ampere. Now the question is, what is the average value of a source current? So means a switch current. Each switch will conduct or each switch will carry inductor current when it is turned on. So switch 1 current waveform will be like this. This is a 0.5 millisecond. This is 1 millisecond. Okay. What is the current here? 25 ampere. This is a switch 1 current waveform. Switch 1 current waveform. Therefore, average value of this switch current is switch current is 25 into function time 0.5 divided by cycle time. So that will give you 12.5 ampere. That will give you 12.5 ampere. So answer for this question is 12.5. Right? So these problems are based on buck converter. Now let us move to the next circuit is that is the boost converter. Next circuit that is the boost converter. So this is based on boost converter. This question is based on boost converter. In the circuit shown in the figure, the switch is operated at a duty cycle ratio of 0.5. A large capacitor is connected across the load. The inductor current is assumed to be continuous. What is the average voltage across the load and average current through the diode? What is average voltage across the load and average current through the diode? Now let us see. Boost converter average load voltage formula will be VDC divided by 1 minus D. It is mentioned duty cycle ratio is 0.5. VDC is equal to 20 volt. So this will be 20 divided by 1 minus 0.5 will give you 40 volt. Will give you 40 volt. Next, the average current through the diode. The average current through diode. Okay. So if you see diode current waveform, diode will carry inductor current when the switch is turned off, right? This is dt and this is t. And what is current flowing through diode? That is IL. This is a diode current waveform. Therefore, in order to find average diode current waveform, you should refer this waveform. Therefore, ID average is equal to, how to find? Area under the waveform, IL into T minus dt divided by T. That means 4 into 1 minus D. D is 0.5. Will give you 2 ampere. Average value of diode current will be 2 ampere and output voltage will be 40 volt. So option C will be the correct answer. Option C will be the correct answer. Right? Let us move to the next question. A DC to DC boost converter as shown in the figure below is used to boost 360 volt to 400 volt at a power level of 4 kilowatt, 4000 watts. All devices are ideal considering continuous inductor current. What is the RMS current in the solid state switch? It's a very interesting problem. Now, first let us see some basic things. Output power is given. What is output power expression? V naught I naught. This is given as a 4000 watt. Output voltage is given as 400 volt. Therefore, from this I will get I naught is equal to 4000 divided by 400, then it is equal to 10 ampere. Excuse me. That will be 10 ampere. Okay, next. The given circuit is boost converter. Therefore, in boost converter, the expression for output voltage is VDC by 1 minus D is equal to V naught. So, 1 minus D is equal to source voltage is how much? 360 divided by V naught is 400. V naught is a 400. Therefore, how much it is? 1 0 cancel. 4 here 9 times, here 10. Therefore, D value is equal to, sorry, 1 minus D value is equal to 0.9 and D is equal to 0.1. Okay. Duty cycle ratio is the 0.1. All right. Now, what is average value of inductor current in this case? I naught boost converter average inductor current is equal to I naught divided by 1 minus D, where I naught is equal to 10 divided by 1 minus D is a 0.9, okay, ampere, right? Or 10 divided by 0.9, 11.11 ampere. 11.11 ampere. Now finally, what we are required to calculate, what is the RMS value of the switch current? So it is mentioned that continuous inductor current, and as the switching frequency is not given, we can assume that inductor current is ripple free. So if you look into switch current waveform, switch will carry the inductor current from 0 to dt. So this is a switch current waveform. Switch current waveform, it will carry inductor current. How much time it will carry? For a time period of dt. Therefore, what is RMS value of this switch current waveform? I switch RMS is equal to magnitude square into function duration, that is dt, divided by cycle time t, total under root. Therefore, IL, what is IL here? 11.11 into root d. D value is equal to 0.1. So, RMS value of switch current is equal to 38, 3.51 ampere. RMS value of switch current is equal to simply 3.51 ampere. This is also PYQ only. Next question. A DC to DC converter is shown in the figure is charging a battery bank B2 whose voltage is constant at 150 volt. B1 is another battery bank whose voltage is a constant at 50 volt. The value of inductor is 5 millihenry and the ideal switch S is operated with a switching frequency of 5 kilohertz. So, switching frequency Fs is given as 5 kilohertz. Therefore, what is one cycle time? 1 by 5000. 200 microsecond. Right? Duty cycle ratio is 0.4. Once the circuit has attained a steady state and assuming the diode D is to be ideal, what is the power transferred from B1 to B2? What is the power transferred from B1 to B2? Therefore, in this case, what you can say here, as per power balance, you can say here P1 is equal to P2. P1 is equal to P2. What is P1? V1 into average inductor current is equal to V2 into average diode current. You can find any one side, you will get the same answer. Okay, whatever the value you want, you can do it. But here let us take some basic calculations. When the switch is on, whenever the switch is on, I can write L into DIL by dt is equal to B1 or V1, that is a 50 volt. Okay, inductor current IL, L di by dt will be subjected to 50 volt. That means DIL by dt is equal to 50 by L. DIL by dt is equal to 50 by L. Okay, next. When switch is off, L into DIL by dt is equal to, if you see the circuit diagram, whenever the switch is turned off, this inductor will be connected to between these two voltage sources, 50 minus 150. 50 minus 150. Therefore, DIL by dt is equal to minus 100 by L. What do you mean by that? Suppose if you see here, based on duty cycle ratio is 0.4, turn on time is 80 microsecond and turn off time will be 120 microsecond. 120 microsecond. Okay. So, in the first 80 microsecond, inductor current is increasing with a slope of 50 by L. In the remaining time, the inductor current is decreasing with a slope of minus 100 by L. Therefore, if you draw inductor current waveform here, it will be like this. This is a IL. So 80 microsecond, let us take x-axis in microsecond. Okay. Inductor current is increasing with a slope of 50 by L, right? Now, when the switch is turned off, it is decreasing with a double slope, right? So, the same waveform will repeat periodically. Now, one important thing here is it stores energy for a time period of 80 microsecond with a rising slope is 50 by L. It is decreasing with a slope double of that. Therefore, this current will come to zero in a half of this time. That means this will be 120 microsecond. Total cycle time will be 200. So next cycle will start from 200 microsecond. This is how inductor current waveform is, right? So this is a discontinuous conduction mode. This is the discontinuous conduction mode. So during turn off time, this slope will be 100 by L. During turn off time, this slope is the 100 by L. Now, if you take this triangle ABC and this is a D, instead of D, let us take E. Okay, so in order to find average value of or power transferred, you need to find average value of this inductor current. So what I can do now, in triangle ABC, you can write down the slope 50 divided by L is equal to BC divided by AC. Therefore, from here BC is equal to 50 divided by inductance. 50 divided by inductance. Inductance value is 5 millihenry. 5 into 10 power minus 3 into AC, where AC is the 80 microsecond. Okay, so let me calculate this. 50 into 80 micro divided by 5 milli. This value is the 0.8 ampere. The peak value of the inductor current is 0.8 ampere. Got it? Finished the question. Now P1 is equal to V1 into average value of the inductor current, where V1 is equal to 50, average value of the inductor current, area under the triangle. Okay, so area under the triangle, half into height 0.8 into base 120 microsecond. Area average value means divided by cycle time, 1 by 200 microsecond. So with this you will get the answer. Just a minute. 39 answer will be 12 watt. So power transferred, even if you want, you can check P2 calculation also, you will get the same answer. But while finding P2, you need to draw diode current waveform. There you have to multiply V2 second voltage multiplied with the average value of the diode current. Okay, I hope this is clear now. All right, let us move further. Next question. A DC to DC boost converter, the duty ratio is controlled to regulate output voltage at 48 volt. Input voltage is 24 volt. Let me write down the data first. Input voltage VDC is equal to 24 volt. Out P0 is equal to V0 into I0 is equal to 120 watt. Switching frequency is 50 kilohertz. Assume ideal components and very large output filter capacitor. The converter operates between boundary between continuous and discontinuous conduction modes. What is the value of boost inductor? Very nice question. So the first thing you have to calculate I0. I0 will be 120 divided by V0. That is a 48. So here 10 times, denominator 4 times. 10 by 4 will give you 2.5 ampere. This is the average value of the output current. Fine. Next, in boost converter, find what is average value of inductor current. I naught divided by 1 minus D. 2.5 divided by, see, input voltage 24, output voltage is 48, means duty cycle ratio is 1 by 2. Okay. Therefore, 1 minus 1 by 2 will give you 5 ampere. Average value of inductor current is equal to 5 ampere. Next, at the boundary condition, at boundary condition, average inductor current IL is equal to delta IL by 2. Average inductor current we got 5. What is delta IL formula? VDC by L, denominator 2 is there, into dt. Into dt. Okay. Therefore, left side is 5, right side source voltage 24 divided by 2 into L. L is to be determined. Duty cycle ratio is equal to 1 by 2 into, what is the frequency here? 50 kilohertz. So, cycle time will be 1 by 50 into 1000. So, by solving this, we will get inductance is equal to, question number 40. It will give you 24 microhenry. 24 microhenry. That is the final answer. Right? This question is based on boost converter. Next problem. Now, buck boost converter. Consider the buck boost converter shown. The switch Q is operated at 25 kilohertz with a duty cycle ratio of 0.75. Frequency frequency is equal to 25 kilohertz. Therefore, cycle time will be 1 by 25 kilohertz. 40 microsecond. Duty cycle ratio D is equal to 0.75. That means 3 by 4. Assume diode and switch to be ideal under steady state condition. What is average current flowing through inductor? Okay, again, very simple question. First thing you have to find average output voltage. VDC into D by 1 minus D. Buck boost converter average output voltage is given by V0 is equal to VDC into D by 1 minus D. So, VDC is equal to 20. D is equal to 3 by 4. 1 minus D will be 1 by 4. So, this will give you average output voltage of 60 volt. Average output voltage of 60 volt. Then average output current I0 is equal to V0 by R. V0 is the 60. Load resistance is 10 ohm. Hence, this will be 6 ampere. Now, the question is, what is the average current flowing through the inductor? Average inductor current is equal to I0 divided by 1 minus D. I0 is 6 divided by 1 minus 3 by 4. So, 1 minus 3 by 4 means denominator 1 by 4. Hence, it will give you average inductor current is equal to 24 ampere. average inductor current is equal to 24 ampere. Okay. Next question. Consider the boost converter shown. I'm sorry, again boost converter came. Okay, fine. Switch Q is operating at 25 kilohertz with a duty cycle of 0.6. Assume the diode and the switch to be ideal. Under steady state condition, what is the average resistance here? So I can say that this average resistance Rin is equal to VDC divided by average value of the source current. If you take average value of source current, it will be very simple, right? So how to find IS? Let us do it one step by step. Duty cycle ratio is given 0.6. Fine. V0 is equal to boost converter VDC divided by 1 minus D. Source voltage is 15 divided by 1 minus 0.6. Okay. 15 by 0.4, 37.5 volt. This is a V0. Next, I0 is equal to V0 by R, where V0 is equal to 37.5 divided by load resistance 10. This will give you 3.75 ampere. Average output current in this circuit is a 3.75 ampere. Next one. Finally, we want IS. So, in case of boost converter, IS is equal to IL, where IL can be expressed as I0 divided by 1 minus D, where I0 is equal to 3.75 divided by 1 minus D value is 0.6. 3.75 divided by 0.4. 9.375 ampere. Okay. Now you will get R in input resistance is equal to source voltage 15 divided by 9.375. This value is equal to 1.6 ohm. Answer for this question is 1.6 ohm, right? Of course, order is slightly missed. Anyhow, this is a boost converter question. Next question. All right. So these are the questions I covered in the three basic DC to DC converters: buck converter, boost converter, and buck boost converter. Okay. Now this concept came based on commutation circuits. So let us read it. The thyristor T in the figure below is initially off and is triggered with a single pulse width of 10 microsecond. It is given that inductor and capacitance values, latching and holding current of thyristors will be 0. How much time the SCR will conduct? Okay. Now in this basic circuit, I can say that expression for current is given by VDC into root of C by L sine of omega t. VDC into root of C by L sine of omega t. How much time SCR will conduct? Until that current has a zero crossing. Until that current has zero crossing. Therefore, conduction time for SCR is omega t is equal to pi, or T on is equal to pi by omega. Okay, in this equation, where omega is equal to 1 by under root LC. Omega is equal to 1 by under root LC. Okay. Therefore, pi into root LC. So, pi into root of inductance value is 100 by pi micro into capacitance value 100 by pi micro. Therefore, how much time SCR will conduct? Pi cancel and it will give you 100 microsecond. Option C will be the correct answer. Option C will be the correct answer. Okay. Now, let us move to the next question. Yes. The figure shows a chopper. The device S1 is the main switching device. S2 is the auxiliary commutation device. This one is a commutation device. S1 is rated for 400 volt 60 ampere. S2 is rated for 400 volt 30 ampere. The load current is 20 ampere. The main device operates with a duty ratio of 0.5. What is the peak current through S1? So in this circuit, whenever S1 is turned on, there are two components of currents that will flow. One component is load current and another component is this resonant current. Okay. This is a IC will also flow through S1, right? Therefore, the peak current flowing through S1, IS1 peak is equal to load current I0 plus resonant peak. Okay. So, I0 plus this resonant peak will be VDC into root of C by L. Let us calculate this. I0 is equal to 20. The resonant peak will be 200 into root of C by L. 2 microfarad divided by 200 microhenry. Therefore, this will be 20 plus 200 into 1 by 100 under root. That means 1 by 10. So, finally, this value you will get it as a 40 ampere. Option D will be correct answer for the question. Option D will be the correct answer. Okay. Let us move to the next question. Now, this question is based on current commutation. This question is based on the current commutation. Now, let us read the question. The circuit in the figure is current commutated DC to DC chopper, where THM is the main thyristor and auxiliary thyristors. The load current is constant at 10 ampere. Main thyristor is on. Auxiliary thyristor is triggered at T is equal to 0. The main thyristor is turned off between. Now, for example, auxiliary thyristor is triggered at a T is equal to 0 here. Whenever auxiliary thyristor is triggered, this is how the resonant current will flow. So, once auxiliary thyristor is triggered, then the main thyristor will turn off only after this sine pulse completed that half cycle. Okay. Therefore, you have to find what is this time. What is this time? Okay. So let me say this is the TA. TA is equal to pi by omega. That will give you pi into root of LC. Pi into root of inductance value 25.28 microhenry into 10 microhenry. Okay. So this will give you, let me calculate this, pi into root of 10 micro into 25.28 micro. So this is a 50 microsecond. Therefore, once auxiliary thyristor is triggered at t is equal to 0, main thyristor will turn off only after 50 microsecond. Only after 50 microsecond, option C will satisfy. Okay, anytime after 50 microsecond. So that is how you can select the option for this question, right? Let us move to the next question. 40 yeah, 46 and 47. I'm sorry here. This is a 46 and 47. Now this is a voltage commutated chopper. A voltage commutated chopper operating at 1 kilohertz is used to control the speed of a DC motor as shown in the figure. The load current is assumed to be constant at 10 ampere. Now the question here is the minimum time in microsecond for which main thyristor should conduct. So the answer here is in voltage commutation, minimum conduction time T on minimum is equal to pi into root of LC. Pi into root of L value 2 millihenry, 2 into 10 power minus 3. Capacitance is 1 microfarad. 10 into 10 power minus 6. So this will give you 140 microsecond. Option B is the correct answer for this question. Sai, no bone చేసి నేను కంటిన్యూ చేస్తాను 2:30 వరకు కంటిన్యూ చేస్తాను అప్పుడు తింటాను నా కర్రీ ఉంటుంది కదా 2:30 తింటా నువ్వు బోన్ చేసి అయిపోతుంది 2:30. So the minimum conduction time will be pi into root of LC in second, right? Now the next question is the average output voltage of the chopper. So in this case, in voltage commutation circuit, V0 is equal to VDC divided by T into T on plus C into 2 VDC divided by I0. Whenever turn on time of the chopper is not given, you can consider this is minimum time. You can consider that is the minimum time. Now if you substitute the data, VDC is equal to 250, cycle time 1 kilohertz. So 250 1 kilohertz means cycle time will be 10 power minus 3. We got minimum turn on time 140 microsecond plus C value 1 microfarad, 10 power minus 6 into 2 VDC, 2 into 250 divided by I0. That is I0 is equal to 10 ampere, I think. 10 ampere, right? So by calculating this, you will get 47.5 volt. 47.5 volt. Okay. Now let us move to the next question. Yeah, this question is based on voltage commutation. This is the question I am telling. This was a very old question. After that, 2006. After that, there is no question from complementary commutation. So it's not that much important. Anyhow, just to touch the concept, we'll see that. Of course, complementary commutation also comes under voltage commutation only, but another name for this is complementary commutation. If the turn-off time of SCR is 50 microsecond and margin of safety is 2, that means circuit turn-off time you can consider margin of safety into thyristor turn-off time. So this will be 100 microsecond. 100 microsecond. What is the approximate minimum value of capacitor required for proper commutation? In complementary commutation, circuit turn-off time can be expressed as RC multiplied with natural logarithm of 2. So from this, you can find capacitance value. C is equal to 100 microsecond divided by resistance is 50 into ln2. So this value will come around 2.88 microfarad. Okay, 2.88 microfarad. So with this, we can conclude these DC to DC converters. That is a chapter 3. Now, before moving to the next topic, we can quickly recap what we discussed so far. So in this chapter, basically there are 3 DC to DC converters. First circuit is buck converter, second one is boost converter, third one is a buck boost converter. After that, you have to look into commutation techniques. In that, voltage commutation and current commutation. Again, in the commutation chapter, only basic thing is just there are 2 formulas. Peak value of the capacitor current, that will be VDC into root of C by L, and the cycle time for that sine pulse to complete pi into root of LC second. Okay. So if you have these 2 formulas in mind, that is more than sufficient. Anyhow, just announcement of short-term program what we are going to take in the month of May and June. Now let us move to 4th chapter. This is the last converter circuits. In this also very simple thing that you have to remember. So single phase voltage source inverters. In that, you just need to look into half bridge and full bridge. Half bridge and full bridge. And the second one is 3 phase full bridge voltage source inverter. In this, you just need to focus into 180-degree conduction and 120-degree conduction. You just need to focus into 180-degree as well as 120-degree conduction. After that, you just need to look into single phase full bridge current source inverter. This is not that much important. And then you need to look into PWM concept. In PWM concept again, single pulse width modulation, multiple pulse width modulation, and sinusoidal PWM, sine PWM. So these are the things that you have to cover in the inverters topic. Okay. Now let us take the questions one by one. Now, very simple question. In the converter circuit, which is nothing but inverter circuit shown below, the switches are controlled such that the load voltage is 400 hertz square wave. What is the RMS value of the fundamental component? So RMS value of fundamental component of the output voltage VO1, it is simply nothing but 2 root 2 by pi VDC, where 2 root 2 by pi value 0.9 into source voltage is 220 volt given. So VDC means this total DC bus voltage. Okay. So this number is 198 volt. Now in case of this circuit, this first section is called a pole. Okay, this is called another pole. If there is only one pole in the circuit, then it is called half bridge VSI. If there are two poles in the circuit, then it is called a full bridge VSI, right? So the output voltage waveform will be a square waveform. If you remember, what are the conclusions for square and quasi-square waveforms? Inverter chapter is very simple. Next, the single phase voltage source inverter is feeding a purely inductive load as shown in the figure. The inverter is operated at 50 hertz 180 degrees square wave mode. Assume that the load current does not have any DC component. What is the peak value of inductor current? So in this circuit, the inductor current waveform, it looks like this. Inductor current waveform is a triangular with the DC component is a 0. If you take x-axis in millisecond, x-axis in millisecond, one cycle time will be 20 millisecond. This will be 10 millisecond. This is a 5. This is a 50. This is the output current. Okay. That is the output current. Inductor value is given as a 0.1 Henry. As the frequency is given 50 hertz, one cycle time will be 1 by 50. That will give you 20 millisecond. Okay. Now, we need to find what is peak value of this output current. In this, the slope of this straight line will be VDC by L. For example, if I take this triangle ABC, if I take the triangle ABC, we can simplify like this. In triangle ABC, the slope VDC by L is equal to opposite side BC divided by AC. Okay. So BC is equal to VDC by L into AC, where BC is nothing but peak value of the output current. Now you just substitute the numbers. Source voltage is given 200 volt divided by inductance is given 0.1 Henry and AC is a 5 millisecond. That means 5 by 1000. Then this is equal to peak value of the output current, you will get 10 ampere. Peak value of this output current is a 10 ampere. This is the answer. Now, let us move to the next question. Yes, this is a very, of course, the slide looks full, but it's very simple question. A three-phase current source inverter is used for speed control in an induction motor, realized using MOSFET switches as shown in the figure. So, one important concept I will write down here. In VSI, the preferable switches are unipolar and bidirectional switches. Okay, that means the switch should have a property like this, unipolar and bidirectional switch. What type of devices are preferable here? A device with body diode. These type of devices are preferable in voltage source inverter. In case of current source inverter, bidirectional and bipolar, bipolar and unidirectional switches are preferable. So the switch properties will be something like this. The switch should be blocking voltage of both the polarities, but current is of only one direction. In that case, we should prefer thyristors, or if you want to use IGBT, you should use a device like this. Okay. So that this type of combination will allow the current to flow in only one direction, but voltage it can block in both the polarities. Therefore, with this concept, you can select here option A is the best suitable for current source inverter. Okay, so this will be bipolar and unidirectional switches, because in this circuit it is given as a current source. So large inductor in series with a DC voltage source will be treated as current source. Large inductor in series with the voltage source will be treated as a current source. Okay, so in current source inverter, bipolar and unidirectional switches are preferable. Now, yeah, this is another interesting thing. Three-phase voltage source inverter is operated in 180-degree conduction mode. Which one of the following statement is true? So, before answering this question, suppose if you look into there are different waveforms: pole voltages, line voltages, and phase voltages in 180 as well as 120-degree conduction. 180-degree conduction, 120-degree conduction. In 180-degree conduction, pole voltages are square waveforms. Line voltages are quasi-square. And phase voltages are six-stepped square. Phase voltages are six-stepped square. Now coming to 120-degree, these two waveforms, I'm sorry, I will write one by one. Pole voltages are quasi-square. Line voltages are six-stepped square. And here also quasi-square. If you practice this table, the next question can be answered very easily. Okay. So now what is the question? So out of all this, only square waveforms will have all odd harmonics, and the remaining all waveforms are having only 6k plus or minus 1 harmonics. Okay. Therefore, now read this one. A three-phase voltage source inverter is operated in 180-degree conduction mode. Which one of the following statements is true? Both pole voltage and line voltages will have third harmonic. See, instead of reading all those things, pole voltages in 180-degree conduction only will have all odd harmonics. Rest of the waveforms are free from triple N harmonics. Okay, so where is that statement? Pole voltage will have third harmonic component. Line voltage will be free from third harmonic. So option B will be the correct answer. For 52, option B will be the correct answer. Let us move to the next question. These are very simple problems. Okay, now in a for a next okay, let us see. In a three-phase inverter circuit shown, the load is balanced and the gating scheme is 180-degree conduction mode. All the switching devices are ideal. Okay, if the DC bus voltage is 300 volt, what is the RMS value of the phase voltage? So in this three-phase inverter circuit for 180 and 120-degree conduction mode, I will suggest you to practice what is the RMS voltages, practice in a small tabular form. So for this particular case, RMS value of the phase voltage is equal to root 2 by 3 into DC bus voltage. Root 2 by 3 into DC bus voltage is given 300. So this is equal to 100 into root 2 volt. 100 into root 2 volt. That is 141.4 volt. 141.4 volt. Okay. Next question. Now in the same circuit, what is the power consumed by three-phase load? So in case of three-phase load, P naught is equal to V phase square divided by R. This is the per phase power multiplied with the 3 because of three phase. Okay. So 3 into, in the previous problem, we got V phase is equal to 100 into root 2 whole square divided by load resistance is how much given? 20 ohm in each phase. This will be 20. Therefore, this answer is 53B. Answer is D, that is a 3 kilowatt. Option D is a correct answer for this question. Okay. Next one. Again, same thing. It is a 120-degree conduction. A three-phase voltage source inverter is supplied from 600 volt DC source shown in the figure for a star connected resistive load of 20 ohm per phase. The load power for 120-degree conduction. So what you have to do here, first find RMS value of the phase voltage. In 120-degree conduction, the formula is VDC divided by root 6. Okay, and P naught is equal to 3 into V phase square divided by R. So this will give you 3 into VDC square, that will be 600 square divided by 6 into 20. So from this, the answer is 54, 9 kilowatt. Answer will be 9 kilowatt. Okay. Srinath, the question is how to find peak inverse voltage of three-phase center tap full wave. There is no center tap in three-phase, sir. All right, now the next question. A three-phase voltage source inverter shown in the figure is feeding a delta connected resistive load. So what you have to do, immediately you should convert this delta into star. right? So this will be in star, it will be 10 ohm, okay. Rest of the procedure is same with 180-degree conduction mode, 180-degree conduction. So P naught is equal to 3 into V phase square divided by R, where V phase is equal to root 2 by 3 into VDC whole square divided by resistance. It is a 10 ohm. If you substitute the numbers, you will get 24 kilowatt. 24 kilowatt. So this is also 180-degree conduction mode. And when delta connected load is given, you have to do like this. So through these three questions, what you have to understand, three-phase voltage or three-phase inverter circuits, there are what type of models? Power calculation or per phase RMS voltage, okay, in both 180-degree as well as 120-degree conduction. And each waveform, what type of harmonics are present? Very simple calculations. If the load is given delta, convert into star. That's it. Only just 4 or 5 questions. If you practice, it is very, very simple, right? Next model. Next model will be PWM technique. Okay, PWM technique. This is also very interesting and a straightforward question. The output voltage of a single phase full bridge voltage source inverter is controlled by a unipolar PWM with a 1 pulse per half cycle for the fundamental RMS component of output voltage to be 75% of DC voltage. What do you mean by that? RMS value of the fundamental output voltage will be 75%. That means 3 by 4 times of VDC. What is the required pulse width? That's it. Now you have to remember Fourier series expression for single pulse width modulation. VO1 is let us write completely. V naught is equal to sigma odd numbers of n 4 VDC divided by n pi into sine of n pi by 2 into sine of nd multiplied with sine of n omega t multiplied with sine of n omega t. Now you have to find RMS value of the fundamental component. VO1 is equal to, first write down the peak value of this, 4 VDC by pi into sine d. This is the RMS, peak value of the fundamental. In order to find RMS value, you have to divide with the root 2. Now, what is the condition given? This is equal to 3 by 4 times of VDC. That's it. 3 by 4 times of VDC. So, you have to find what is the pulse width. So, let us simplify this first. So, you can cancel VDC on both sides first. Okay. So, sine D is equal to 3 by 4 means 0.75. 4 by root 2 pi means 0.9. From this, you will get D value. D value is equal to sine inverse 0.75 divided by 0.9. This is the 56.44 degree. Therefore, pulse width is equal to 2D. That means 112.9 degree. 112.9 degree. That is a pulse width answer. So 56 question, 112.9 degree is the pulse width. Next. So this is a very another straightforward question. An inverter has a periodic output voltage with an output voltage waveform as shown in the figure. Okay. So this alpha is given. This alpha is nothing but pulse width in this problem. When the conduction angle alpha is equal to 120 degree, which is nothing but pulse width, what is the fundamental component of output voltage? So fundamental component, RMS value of the fundamental component, VO1 is equal to 4 VDC by pi into sine D, right? So sine D is nothing but half of the pulse duration divided by root 2, RMS value. That means 2 root 2 by pi, VDC as per the question it is given as 1 into sine, you have to substitute here 60, not 120. 120 is the pulse width. In that expression, D is nothing but half of the pulse width. When the pulse width is 2D, in that expression you have D. Therefore, you will get this equation is equal to 0.78. Option A is the correct answer for this question. Okay. Next. Now, again, in the PWM topic, there is another important question. In order to eliminate nth harmonic, to eliminate nth harmonic, required pulse width is equal to 2 pi by n. Very, very important objective question. Now, with reference to the output voltage given in the figure, the output of the converter will be free from fifth harmonic when pulse width alpha is equal to 2 pi by 5. That will be 72 degree. That will be 72 degree. Okay. Now the next question. Now these models are very important and quite common in gate questions. The switches T1 and T2 in the figure are switched in a complementary fashion with a sinusoidal pulse width modulation technique. The modulating voltage, this one, let us write that in the next slide. Modulating voltage is equal to 0.8 sine of 200 pi t. 200 pi t volt. That means output frequency at fundamental component is the 100 hertz. This is what indirectly given in the question. And the triangular carrier, the carrier frequency is of 5 hertz. What is the peak value of the 100 hertz component of the load current? So that is what asking here. So what is that means? Modulation index is equal to 0.8, this number. Okay. What is that modulation index? That is given nothing but 0.8. So peak value of 100 hertz component of the load current. That means what is the peak value of the fundamental load current? That is nothing but VO1 peak divided by Z1. VO1 peak divided by Z1. Okay. So what is VO1 peak? Modulation index into VDC by 2 in half bridge VSA. Denominator is Z1. Let us substitute these values. Modulation index is given 0.8 and VDC by 2 is 250 volt divided by root of Z1. Z1 is nothing but 12 square plus 16 square. Right? So this will be 59. Let me calculate. 0.8 into 250 divided by root of 12 square plus 16 square, 10 ampere. Okay, so this answer will be 10 ampere. So this is the answer for the question. Okay, next one. This is also in almost a similar model. So the figure below shows half-bridge voltage source inverter supplying an RL load. R is equal to 40 and inductance value is 0.3 by pi Henry. The desired fundamental frequency of the load voltage is 50 Hertz. So with that, let us do simple calculations. Frequency is of 50 Hertz. That means omega is equal to 100 pi radian per second. Therefore, load fundamental frequency will be, load impedance at fundamental frequency will be root of R square plus XL square, where resistance is the 40 plus 30 square. This will give you 50 ohm. Okay, this is a load impedance at fundamental frequency. Next one. The switch control signals of the converter are generated using sinusoidal pulse width modulation, whose modulation index is 0.6. MA is equal to 0.6. At 50 Hertz, the RL load draws an active power of 1440 watt, 1.44 kilowatt. What is the value of this DC source voltage? Okay, so PO1, how to express this? IO1 square into R. This value is given 1440 watt. That value is given as a 1440 watt. Therefore, RMS value of the fundamental load current will be 1440 divided by 40 under root. That means this value will be root 36, will give you 6 ampere. But what is this IO1? IO1 is nothing but RMS value of the fundamental voltage divided by Z1. Okay, RMS value of the fundamental voltage divided by Z1. But what is RMS value of this fundamental voltage? MA into VDC as per the given question. Okay, strictly speaking, it is VDC by 2. VDC by 2 means this part. So you have to take that value divided by Z1. Now this is a peak value. Denominator you have to take a root 2 into Z1 is a 50 is equal to 6 ampere. So from this, modulation index is 0.6. You have to calculate VDC is equal to 6 into 50 into root 2. Therefore, VDC, which is a half of the DC bus voltage, will give you 500 into root 2 volt. 500 into root 2 volt. Okay. This is this question. So these two models are very important. That is what we covered. I hope these models will give you a good quick revision for this thing. Now this is again another announcement. So with that I can cover, I can conclude the quick revision of DC to AC converters, and that is about inverters. Now AC voltage regulator, one model you just practice. Strictly speaking, it is not in the syllabus, but you just practice this one model. What is that? Now this RL load, okay, this RL load, it is very, very important. In the single phase voltage controller circuit shown in the figure, for what range of alpha the output voltage is not controllable. Okay, in this case, if the load is RL load, RL type. Then output voltage V0 is controllable when alpha is greater than load power factor angle. When alpha is greater than load power factor angle. Okay, where phi is equal to tan inverse omega L divided by R, where phi is equal to tan inverse omega L divided by R. Now, in this question, what is phi value? Tan inverse omega L is 50, load resistance is also 50. Therefore, this value is a 45 degree. So, if at all firing angle is less than 45 degree, then output voltage cannot be controlled. Okay. So, as it is question is not controllable, therefore you have to consider whenever firing angle is less than 45 degree, then output voltage cannot be controlled. So, only this model, if you quickly revise in AC voltage regulator, that is more than sufficient. I hope with this we came to an end. So with this I will conclude. So again, quickly recap what we discussed so far. If you go to the first thing, in case of power electronics, total syllabus is divided into 4 topics. One is basics and power semiconductor devices overview. Second chapter is rectifiers, single phase and 3-phase rectifiers. Third chapter, DC to DC converters, and fourth chapter, DC to AC converters. If you are preparing for PSU exams, AE and AEE, you should also prepare AC voltage regulators, cyclo converters, and drives. Okay, these are extra topics. These topics are not required for GATE exam because they are not in the syllabus. With this, I will conclude today. I wish you all the best. So if anyone is interested for the upcoming batches, as per the slides shown in this presentation, please go through that, and I will show once again. You can feel free to contact whatever the number. I think the number is not given here. You may feel free to contact this number, right? So here also number is not there. Yes, you can contact this number. Please note down this number, 95156 94053. So with this I will conclude for today. I wish you all the best. Thank you.